Hello there and welcome to Science for Sleep, where curiosity drifts gently through the cosmos and science settles into a calm rhythm fit for rest. Tonight we'll be taking a journey into one of the most astonishing, bewildering and quietly terrifying corners of the universe. A place where the ordinary rules of matter are twisted, where gravity crushes atoms into unfamiliar shapes, and where stars that once burned brightly live on as dense remnants smaller than a city yet heavier than the sun. We are talking about neutron stars. They are sometimes described as the deadliest objects in existence. But don't worry, none are close enough to trouble us tonight. For now, they're a safe distance away, far across the galactic sea, and we can explore them from the comfort of imagination. Before we set off, let me ask you something. Where in the world are you listening from tonight? Is it evening where you are? Perhaps with the day's sounds fading and the sky already dark? Or maybe it's morning and you're greeting the day with this voice accompanying you like a background hum. Time zones scatter us, yet here we are together, connected through a single thought about the universe. If you find this little voyage soothing, or if it simply helps you wind down, I'd be grateful if you gently tap the like button, maybe even subscribe so others who might need a calm pause can find it too. So get comfortable, let your thoughts ease, and let's begin. Because somewhere out there, scattered like invisible embers in the blackness, are stars that died and yet refuse to fade entirely. Their story is violent, their nature is extreme, and yet their existence reveals so much about the fabric of reality. Imagine for a moment the life of a massive star, not one like our Sun, which is stable and calm by comparison, but one many times larger, blazing hotter and brighter. A star like this lives fast and dies young. Its lifetime is measured in millions of years, not billions. For a while it maintains a delicate balance, its outward pressure from nuclear fusion holding back the inward pull of gravity. But gravity is relentless. It always waits. And when the star's fuel runs out, when there is no more nuclear fire to hold it open, gravity wins. The star collapses in on itself, imploding with such violence that its outer layers blast away in a supernova. The core that remains is crushed beyond comprehension, and in that collapse lies the birth of a neutron star. Now, it's one thing to say, a star collapses, but let's consider what that really means. Picture something the size of our Sun, a sphere nearly 1,000,000 miles across. Imagine all of that matter being squeezed down until it's only about 12 miles wide. That's about the size of a city, something you could cross in less than an hour by car. Yet this tiny sphere still contains more mass than the Sun. 1 teaspoon of it would weigh billions of tons on Earth. Matter in this form no longer resembles anything familiar. The protons and electrons that once danced freely are forced together into neutrons, packed shoulder to shoulder until there is no more room. This strange remnant is not simply a small star. It's a whole new category of object, balanced on the razor's edge between existence and collapse. If the mass is a bit higher, it could fall into itself completely and become a black hole. If it's a bit lower, it may remain as a white dwarf. But in this precise extreme range, it becomes something in between, dense enough to warp space and time, yet still visible, still radiating energy, still leaving its mark on the universe. You might wonder why they're sometimes called the deadliest. Part of the answer is simply their density. Get too close to a neutron star and the difference in gravitational pull between your head and your feet would tear you apart in an instant. That effect is called spaghettification, though the name doesn't really convey the horror of what it means. Their magnetic fields are so powerful that they can strip electrons off atoms from thousands of miles away. Some neutron stars emit beams of radiation that sweep across space like cosmic lighthouses. If Earth were in their path, life as we know it would be in jeopardy. They are extreme in every possible way, but tonight we'll explore them gently, at a safe distance, with awe rather than fear. Think of them as laboratories of physics. They allow us to glimpse matter under conditions that can never be recreated on Earth. By studying them, astronomers uncover secrets about the fundamental forces of nature, and while they're deadly in theory, in practice they're simply too far away to trouble us. Instead, they exist as reminders of the vast, strange universe we live in. Even as we talk about them, it's worth pausing for a moment. Somewhere, in a distant patch of sky, a neutron star spins silently, unseen by most, unnoticed except by careful instruments. It's easy to forget that such things exist at all, given how distant and abstract they sound. Yet they are real, each one a monument to the death of a massive star, each one a marker in the history of the cosmos. Their story doesn't end with their birth. Some spin at incredible speeds, hundreds of times each second, faster than a kitchen blender. Some generate magnetic fields 1,000,000,000,000 times stronger than Earth's. Some merge together in violent collisions, creating bursts of energy so intense they outshine entire galaxies. And from those collisions, elements like gold and platinum are scattered into space, seeding future stars and planets. When you hold a piece of jewellery, you're holding the remains of a star's death throes. Neutron stars might be deadly, but they are also generous. Without them, many of the elements that make up our world would never exist. Life as we know it might never have arisen. Never. It's a strange paradox that the most violent ends of stars give rise to the raw materials for new beginnings. As we drift deeper into this story, keep in mind the scale. These are not just curiosities. They are part of the great cycle of stellar life and death. They shape galaxies, they ripple space-time, and they remind us of the vast power of nature. And so, as we ease further into the night, imagine yourself watching a star collapse, watching its brilliance fade, and knowing that what remains is not an ending, but a transformation. That transformation is where we'll stay for a while, exploring every layer of what it means to be a neutron star. Because in their density, their violence, and their mystery, they may just hold answers to some of the most profound questions we can ask about the universe. When you picture the night sky, it's easy to think of stars as eternal. They shine with such steadiness that from one lifetime to the next they seem unchanged. Yet every star has a story, and like any story it has a beginning, a middle, and eventually an end. The most massive stars, the ones many times larger than our Sun, live especially dramatic lives. Their births are violent, their youth is extravagant, and their deaths are among the most spectacular events in the universe. To understand where neutron stars come from, we need to follow the journey of one of these giants, from its bright beginnings to the moment it collapses in on itself. Stars are born from clouds of gas and dust, the raw material of the cosmos. Gravity gathers these clouds together, pulling atoms closer until they heat up and ignite nuclear fusion. Once fusion begins, a star is alive in the truest sense we can use that word for an object of plasma. Hydrogen atoms fuse to form helium, releasing light and heat that radiates across space. In a star like our Sun, this process is balanced and stable, allowing it to shine for billions of years. But in a giant star, the kind we're interested in tonight, things happen faster and with more intensity. A massive star burns its fuel at a furious rate. Its light is brighter, its temperature hotter, and its lifetime shorter. Instead of billions of years, it may last only a few million. That sounds long to us, but on cosmic scales it's brief, almost like a spark compared to a slow, glowing ember. The reason is simple. Gravity pulls more strongly on a massive star, and to resist that pull, the star must generate greater pressure from fusion. That means it consumes its hydrogen more quickly, racing through its supply like a bonfire that devours wood. As the hydrogen runs out, the star turns to new fuel. Helium becomes carbon, carbon becomes oxygen, and so on, building heavier and heavier elements in its core. Each stage happens more quickly than the last, as if the star is sprinting toward a finish line it cannot avoid. By the time iron begins to form, the star has reached a dead end. Iron cannot release energy through fusion. It costs more energy to fuse than it produces. For the star, this is the moment of crisis. Without new energy to push outward, gravity gains the upper hand. The balance that has held for millions of years breaks. The star's core begins to collapse inward, compressing under its own weight. Imagine a sphere the size of the Earth's orbit suddenly giving way, its mass rushing inward at a significant fraction of the speed of light. Temperatures soar to billions of degrees. The outer layers, unable to resist, fall inward as well, then rebound in a massive explosion. This is a supernova, one of the most powerful events in the cosmos, bright enough to outshine an entire galaxy for a brief time. Supernovae are not just fireworks. They are creative acts as well as destructive ones. The shockwave from the explosion forges new elements, scattering them into space. Gold, silver, uranium, and countless others are born in this chaos. Every heavy atom in your body, every trace of iron in your blood or calcium in your bones, was forged in the death of a star. We are quite literally made of stellar remnants. That poetic truth is grounded in physics, but what of the core that triggered it all? That collapsed heart of the giant? Here, the story narrows to a scale almost impossible to imagine. The inward collapse squeezes protons and electrons together, creating neutrons. In fractions of a second, the core becomes a sphere of neutron-rich matter, only about a dozen miles across, yet still holding more mass than the Sun. The density is so extreme that normal language fails to capture it. Saying that a teaspoon of this matter weighs billions of tons is true, but even that metaphor is difficult to picture. Imagine taking all the mountains on Earth and compressing them into something that fits in your hand. That is the density of neutron star material. This object, this collapsed core, does not continue collapsing indefinitely because something resists. The neutrons themselves, governed by quantum mechanics, push back against further compression. This push is not like any ordinary force. It arises from the rules that particles follow, rules that prevent them from all occupying the same state. This resistance halts the collapse, at least temporarily. If the star's mass is within a certain range, the core stabilizes as a neutron star. If it is greater, even this resistance is not enough, and the collapse continues until a black hole forms. For those that survive as neutron stars, the transformation is complete. The brilliant bloated giant is gone, and in its place is a tiny, dark, unimaginably dense sphere. It no longer shines like an ordinary star, but it is far from lifeless. It can spin, it can radiate beams of energy, it can quake and ripple with magnetic storms. It is the corpse of a star, yet in many ways it is more active than the star ever was. Consider the violence of that transition. A massive star, steady in the sky for millions of years, suddenly collapses and explodes in just seconds. In that brief moment, it releases more energy than our Sun will in its entire lifetime. The core that remains is so dense that space-time itself bends sharply around it. Light passing nearby curves, and time runs more slowly close to its surface. It is a place where the familiar rules of the world we know are stretched into strange shapes. You might imagine this collapse as rare, but in our galaxy alone it has happened countless times. Astronomers estimate that hundreds of millions of neutron stars exist in the Milky Way. Most are invisible to us, silent and dark, but some reveal themselves through bursts of radiation or rhythmic pulses of radio waves. These are the pulsars, the cosmic lighthouses which we'll wander towards soon enough. For now, it is enough to know that every one of them is the grave of a giant star, a reminder that even the brightest lives come to an end. Yet calling it an end feels misleading. What remains is not nothing. It is something new, something strange, something that continues to affect its surroundings in profound ways. Neutron stars are like fossils of physics, preserving conditions that cannot be recreated in any laboratory. By studying them, we gain insights into the behaviour of matter at densities far beyond anything on Earth. They show us how nature behaves when pushed to its absolute limits. If you look up at the night sky and see the soft glow of stars, it's hard to connect that beauty with the violence of collapse. And yet, hidden among those points of light are the remnants of explosions long past. Somewhere in the constellation of Cassiopeia there is the famous Crab Nebula, the expanding cloud of a supernova recorded by Chinese astronomers in the year 1054. At its centre lies a neutron star spinning 30 times a second, still radiating after nearly 1,000 years. That remnant, small and dense, is the collapsed heart of a giant. This cycle of life and death, of birth, collapse and transformation, continues throughout the universe. Stars form, they burn, they die, and from their ashes come neutron stars, black holes, and the seeds for new generations. The collapse of giants is not just a curiosity of astrophysics, it is the mechanism by which the universe renews itself. Every heavy atom around you is proof of this. The story of neutron stars is not just out there in space, it is written in your bones, in your blood, in the world around you. And so, as we move forward, remember that a neutron star is not merely a collapsed object. It is the testimony of a life once lived, a blazing star that shone, collapsed, and left behind something stranger and denser than we can truly imagine. These remnants are the bridge between the ordinary stars we see and the mysteries of space-time itself. They are both an ending and a beginning, a paradox made real. When you hear that a neutron star holds more mass than the Sun inside something no larger than a city, it sounds like exaggeration, a kind of cosmic metaphor. But it is not a metaphor at all. It is a straightforward fact of physics, one of those truths so extreme it feels unreal. Imagine taking everything the Sun contains, all of its hydrogen and helium, all of its burning layers, all of its mass that stretches nearly 1,000,000 miles from side to side, and then pressing it down until the entire object fits comfortably inside the area of a large metropolitan skyline. That is the scale we are dealing with. To make sense of it, let's start with the Sun itself. Our Sun weighs about 2 nonillion kilograms. That's a 2 followed by 30 zeros. A number too large to picture, but enough to understand that we are dealing with something massive. The Sun is so heavy that its gravity holds the planets in orbit, and it makes up more than 99% of the total mass of our solar system. Yet if a star slightly larger than the Sun ends its life in collapse, much of its material will be blown outward in the supernova, leaving behind a core that still weighs more than our star but occupies a space just a few miles wide. That compact core is the neutron star. Now imagine something only about 12 miles across. If you were standing on one side of it, you could walk to the other in just a few hours, yet beneath your feet would be mass equal to or greater than our entire Sun. On Earth, the densest material we encounter is the nucleus of atoms, but in ordinary matter those nuclei are separated by clouds of electrons, with mostly empty space in between. In a neutron star, that empty space is gone. Gravity has crushed everything together until protons and electrons have combined into neutrons. The result is matter in its most tightly packed state, short of becoming a black hole. It's tempting to try to picture holding a piece of such matter in your hand. Scientists often say that a teaspoon of neutron star material would weigh billions of tons. That description is true, but even it understates the reality. 1 billion tons is the weight of mountains. Imagine setting something that heavy on a kitchen scale, or even on the ground beneath you. It would tear through the surface, sinking instantly to the centre of the Earth. In fact, it's impossible to isolate a piece of neutron star matter outside its environment. The moment it left the crushing gravity and pressure that holds it together, it would explode outward violently, unable to exist under ordinary conditions. Still, the comparison helps us imagine just how alien neutron stars are. They are not simply dense rocks floating in space. They are objects where the structure of matter itself has changed. Quantum physics rules their interiors. Neutrons are crowded shoulder to shoulder, and their interactions create pressures strong enough to resist further collapse. Even so, if the mass of the star is just a little higher than this balance point allows, nothing can stop the implosion. In that case, the core becomes a black hole instead. The neutron star exists only in this narrow band of possibility, teetering on the edge between stability and collapse. Now think about what it would mean to stand on the surface of such an object. Not that you could in any practical sense, but consider the gravity there. On Earth, we are held down by a comfortable pull. On a neutron star, the pull would be about 200 billion times stronger. Drop something from your hand, and it would reach the surface in less than a microsecond, striking with unimaginable energy. If you somehow survived arriving there, you would weigh more than a mountain. Your body would be torn apart long before you had time to realize it. And yet, in the calm of thought, we can imagine it safely. We can consider what it means for matter to be so compressed. It forces us to realize that the world we experience every day is mostly empty space. Atoms are vast compared to their nuclei. The solidity we feel when we touch a table or a wall is the result of electromagnetic forces, not solid matter pressing against solid matter. In a neutron star, that empty space is gone, leaving behind only the dense heart of matter itself. It is like stripping away the illusion and seeing the true weight of the universe. Astronomers measure neutron stars with delicate precision. They study how fast they spin, how they bend light, how they tug on nearby companions. From these observations, they can estimate their masses and sizes. The results are consistent. Neutron stars typically pack between 1.4 and 2 times the mass of the Sun into a sphere no wider than a small city. That ratio of mass to volume is unlike anything else. Even white dwarfs, which are themselves incredibly dense, cannot compare. If the Earth were compressed to the density of a neutron star, it would be the size of a small marble. Think of an ordinary city for comparison. Imagine New York or Tokyo, Paris or Sao Paulo. Stretch across the skyline from one side to the other, maybe 10 or 15 miles. Now imagine that the entire Sun has been squeezed into that same footprint. A whole star, once glowing across space, is now a tiny dot compared to its former self. It is an almost absurd picture, yet it is real. The universe contains countless such objects. They spin in silence, they drift among the stars, and their presence is known only through the signals they send and the distortions they create in the fabric of space around them. There is a strange symmetry here. Stars that are too light never collapse into neutron stars. Stars that are too heavy go further, becoming black holes. Only in the middle, in that narrow range of mass, do we find these incredible remnants. They are the balance point, the knife edge, the compromise between extremes. In some sense, they are rare survivors. A little lighter and they would not exist. A little heavier and they would vanish into a horizon from which nothing returns. What's more, the structure inside them remains one of the greatest mysteries of modern physics. We can describe their crust, which is thought to be a thin shell of ordinary atomic nuclei crushed into a crystalline lattice. We can describe the layers just beneath, where neutrons begin to drip free and form strange fluids. But deeper still, we enter the realm of speculation. Some scientists suggest that within the core, neutrons break down into their constituent quarks, creating quark matter or even exotic phases unknown on Earth. Others believe that hyperons, particles containing strange quarks, may appear. These possibilities are difficult to test, but neutron stars offer the only natural laboratories where such conditions can exist. By studying them, we hope to learn more about the fundamental forces that govern matter. Observations of their spin rates, their magnetic fields, and their collisions with one another provide data that helps refine our theories. In 2017, for instance, astronomers detected gravitational waves from 2 neutron stars merging. That event revealed not only the staggering energy of their collisions, but also new insights into the behaviour of matter under pressure far beyond any laboratory experiment. It showed us that even the heaviest elements like gold and platinum are produced in such events. What we wear as ornaments began as the wreckage of neutron stars. The weight of a sun in a city is not just a curiosity, it is a gateway to deeper questions. Why does matter behave as it does? What are the ultimate building blocks of nature? How far can the laws of physics stretch before they break? Neutron stars press us to confront these questions, and they do so while lying quietly in the night sky, often invisible to the eye. Their existence tells us that the universe is capable of extremes far beyond our ordinary experience. When we consider them, it is tempting to dwell on their violence, their density, their danger, but it is also worth considering their role in the grand cycle of the cosmos. Without their collapse, without their extreme compression, we would not have the elements we need for life. We would not have the richness of the world we live in. In their destruction, they create. In their compactness, they reveal the structure of matter. And in their silence, they remind us of the vast, unyielding power of gravity. So the phrase, "the weight of a sun in a city," is not exaggeration. It is the most literal description possible of what a neutron star is. A sun's worth of mass, squeezed down until it fits where skyscrapers rise, where traffic flows, where people walk from block to block. It is an image that stretches imagination to the breaking point, but it is real. And out there, scattered across the galaxy, millions of such objects spin quietly, invisible to most of us, but deeply woven into the story of the universe. When you think about gravity here on Earth, it feels gentle. It keeps your feet on the ground, holds the oceans in place, and tugs the air around us into a breathable blanket. You can jump, you can run, you can climb, and though gravity always pulls you back, it does so with a strength that feels manageable. We build skyscrapers that resist it, planes that temporarily overcome it, rockets that claw their way free of it. It is present in every moment of life, but it never feels impossible. That is because Earth's gravity, while it defines our world, is weak compared to what is possible. A neutron star reveals this difference more dramatically than any comparison we can make. Imagine standing on the surface of Earth. If you wanted to escape its pull entirely, you would need to reach a speed of about 11 kilometers per second, roughly 25,000 miles per hour. That's the escape velocity, the speed needed to leave Earth behind forever without further propulsion. It's fast, but with modern rockets it's achievable. Now picture a neutron star. Its escape velocity is more than half the speed of light. Not thousands of miles per hour, but hundreds of thousands of miles per second. Nothing short of light itself can even approach it, and even light feels the strain. If you were somehow standing on the surface and tried to jump, you wouldn't rise even the thickness of an atom. Gravity's grip there is so absolute that motion becomes nearly impossible in any direction but downward. This overwhelming pull is not simply a matter of strength. It is the natural outcome of compressing so much mass into such a tiny space. The Sun, spread out over nearly 1 million miles, holds its matter at a relatively relaxed distance from its centre. A neutron star, with that same amount of mass squeezed into a dozen miles, focuses its gravity intensely. The curvature of space-time around it is steep, as if the fabric of the universe itself has been pulled taut and bent inward. To move near it is to slide downhill into a well so deep that climbing back out becomes nearly impossible. Even before you reached its surface, the effects would begin. As you approached, you would feel tidal forces pulling at you unevenly. Your feet, closer to the star, would be yanked more strongly than your head. On Earth, this difference is negligible. Near a neutron star, it becomes lethal. Your body would stretch, distort, and tear apart long before you touch down. Astronomers sometimes call this spaghettification, a term that almost trivializes the violence of the process. It is not simply a stretching, but a shredding, the result of gravity's grip being so uneven across even small distances. And yet, despite its danger, this gravity is not hostile, it is not malevolent, it is simply gravity pushed to an extreme. It follows the same rules that hold the planets around the Sun and the Moon around Earth. It is the same force that pulled you down as a child when you jumped from a swing. The difference is scale. A neutron star shows what gravity can do when mass is concentrated to the limits of possibility. It demonstrates the raw, uncompromising side of a force we often take for granted. Consider what happens when light itself passes near such an object. Normally light travels in straight lines, unaffected by ordinary pulls and pushes. But in the warped space around a neutron star, those straight lines bend. Photons curve, their paths distorted by the intense curvature of space-time. This bending can create strange optical effects, where the star appears larger than it is, or where light from its far side loops around so that you can see more than half of its surface at once. If the neutron star is paired with another star, the light from that companion can be warped into arcs and rings. These gravitational lensing effects are subtle at cosmic distances, but they reveal just how profoundly space is twisted by the presence of so much mass. Now think about time itself near such a star. According to general relativity, gravity does more than bend space. It slows time. The deeper you are in a gravitational well, the more slowly time passes relative to someone far away. On Earth, the difference is tiny. A clock at sea level ticks slightly slower than a clock on a mountaintop, but the difference is measured in billionths of a second. Near a neutron star, the effect is profound. A clock on its surface could tick at a noticeably different rate compared to one orbiting at a safe distance. To an outside observer, processes on the surface would appear slowed. To someone there, everything would feel normal, but the universe beyond would seem to race ahead. Gravity grips not just space, but time itself. The strength of this grip also influences what happens around the star. If gas or dust from a companion star is drawn into its orbit, it forms an accretion disk. This material spirals inward, accelerating and heating as it falls. The gravity tears it apart, compressing and superheating it until it glows in X-rays. These emissions can be detected across vast distances, allowing astronomers to identify neutron stars that would otherwise be invisible. The grip of gravity in this way becomes a beacon, not because the neutron star shines on its own, but because it transforms anything that falls into its influence into light. The pull is so strong that it defines boundaries. If you approach too closely, there is no turning back. For a neutron star, this boundary is not as final as the event horizon of a black hole, but it is still formidable. Crossing into its immediate environment means confronting forces beyond comprehension. Nothing escapes easily, not even radiation. Energy leaving its surface is red-shifted, stretched into longer wavelengths as it fights against the pull. Photons climb uphill, losing energy, dimming by the time they reach the outside universe. What we observe from a distance is always less than what is truly happening there. It might seem abstract, but gravity's grip is something you can feel in the imagination, if not in reality. Picture standing on Earth with the faint tug holding you close. Now multiply it, not by 10 or 100, but by billions. Imagine that every movement downward is inevitable, that no rocket could lift you free, that no engine could provide enough thrust. You're locked in place by the sheer density of matter below you. That is the environment of a neutron star. It is a reminder that gravity, though invisible, is the most dominant sculptor of the universe. When two neutron stars orbit each other, their mutual grip creates spirals of energy. They lose momentum as gravitational waves ripple outward, and slowly, over millions of years, they draw closer. Eventually they merge, releasing energy so vast it shakes the very fabric of space-time across galaxies. Observers on Earth, with sensitive detectors, can measure these ripples. They arrive as tiny vibrations, stretching and compressing space by less than the width of a proton. Yet those faint tremors come from events where gravity's grip was so strong that stars themselves were torn apart. This is what it means for nothing to escape easily. It is not just that matter cannot flee, but that light itself struggles, that time itself slows, that even stable orbits decay under the relentless pull. Gravity is not simply stronger here. It is absolute in a way that redefines what we think possible, and still, it is the same familiar force, the same gentle tug that pulls an apple from a tree. Scaled up, compressed, focused, it becomes the master of stars. The idea that gravity grips so fiercely that escape requires the speed of light also hints at the boundary between neutron stars and black holes. If the mass is just a little higher, the grip tightens further. Eventually, not even light has enough speed to leave. That is the threshold at which a neutron star can no longer resist and collapses into a black hole. In this sense, neutron stars are the last step before absolute captivity, the final state where matter is still visible, still tangible in some form, before it disappears entirely from view. So when astronomers describe these objects as compact, dense and extreme, it is not hyperbole. They are literally places where gravity has reached nearly its maximum possible strength without breaking through into the domain of black holes. They are thresholds, balancing points, natural demonstrations of how far the laws of physics can be pushed. Their gravity is the defining feature, the grip that shapes everything around them, the pull that ensures nothing nearby remains unchanged. Even from the quiet of imagination, it's possible to sit with that thought for a while. Gravity that makes time itself slow. Gravity that bends light into curves. Gravity that can tear apart atoms, matter, and even stars. It is not something we need to fear in our daily lives, but it is something worth respecting, a reminder of how different the universe can be beyond the familiar scale of Earth. When neutron stars were first theorized, no one expected they would become some of the most reliable clocks in the universe. The idea that a dead star could spin in perfect rhythm, sending beams of energy across space with more consistency than any human-built machine, was beyond imagination. Yet in the late 1960s, astronomers stumbled upon signals that seemed almost artificial in their precision. They were radio pulses, arriving at intervals so regular that the first thought was that perhaps they came from some kind of extraterrestrial civilization. The signals were jokingly labelled LGM, short for little green men. But as the evidence grew, it became clear these were not messages from alien neighbours. They were the voices of neutron stars speaking in the only language they could. Radiation sweeping past like the beam of a lighthouse. These objects became known as pulsars. A pulsar is simply a neutron star with a special orientation. Imagine that the star is spinning rapidly, sometimes dozens or even hundreds of times every second. It also has a magnetic field, so intense that particles are accelerated near its poles. These particles emit beams of electromagnetic radiation, often in the radio part of the spectrum, but sometimes in visible light, X-rays, or even gamma rays. If those beams happen to sweep past Earth, we detect them as regular pulses. Just as a lighthouse on a rocky coast sweeps its light across the sea, so a pulsar sweeps its signal across the cosmos. The rotation is steady, the beam narrow, and from our perspective it looks like a flashing beacon in the dark. What makes pulsars so remarkable is not just that they exist, but how precise they are. Some rotate with the steadiness of atomic clocks. Their pulses arrive with such accuracy that astronomers can predict them to within millionths of a second. In some cases, they are used as cosmic timekeepers, helping measure distances, gravitational waves, and even testing theories of relativity. It is astonishing that the collapsed remnant of a massive star, something born out of chaos and destruction, can become one of the most stable natural metronomes in the universe. To appreciate this, think of how they spin. When a star collapses into a neutron star, it shrinks dramatically. Just as a figure skater spins faster when pulling in their arms, the collapsing star spins faster as it contracts. What once was a slow rotation becomes a furious whirl. Some pulsars rotate several times each second, while the fastest known spin hundreds of times per second. That's a dead star rotating faster than the blades of a household blender, faster than the wheels of a high-speed turbine. And yet, despite such rapid rotation, they remain stable for millions of years, gradually slowing only as they lose energy through radiation. The Crab pulsar is one of the most famous examples. It sits at the centre of the Crab Nebula, the remains of a supernova witnessed on Earth nearly 1,000 years ago. This pulsar spins about 30 times per second, sending out pulses that have been detected not just in radio waves but in visible light as well. If you had the right equipment, you could actually watch its flashes in real time, blinking steadily in the darkness. That blinking is the heart of a collapsed giant, still announcing its presence long after its outer layers were blown into space. Some pulsars are even more exotic. Millisecond pulsars, for example, rotate hundreds of times per second. These extreme speeds are thought to come from interactions with companion stars. Over time, matter from the companion can fall onto the neutron star, transferring angular momentum and spinning it up like a cosmic flywheel. The result is an object no bigger than a city, rotating so fast it completes more than 700 revolutions each second. And still, it does not fly apart. Its gravity and structural rigidity are strong enough to hold it together against centrifugal forces that would tear apart anything else. The beams themselves are fascinating too. They are not simple flashes of light. They are the product of intense magnetic fields and charged particles moving at nearly the speed of the light. The geometry of how those beams are aligned determines whether we see the pulsar at all. Many neutron stars may spin and emit beams, but unless those beams happen to cross Earth's line of sight, they remain invisible to us. What we call a pulsar is as much about perspective as it is about physics. It is our particular vantage point that lets us hear the beat of their rotation. Pulsars have taught us much about the universe. In 1974, 2 astronomers discovered a pulsar in a binary system, orbiting another neutron star. By studying the timing of its pulses, they confirmed one of the predictions of Einstein's general relativity, that orbiting masses emit gravitational waves, losing energy and drawing closer together. This was decades before gravitational waves were directly detected, yet pulsars had already provided the first indirect proof. Their steady rhythms became tools for exploring deep truths about space-time. Beyond testing physics, pulsars serve as markers. Some astronomers have even proposed that we could use them as a kind of galactic GPS system. Their pulses are so regular and distinct that a spacecraft equipped to detect them could navigate across interstellar distances by comparing its observations with known pulsar catalogues. In fact, when the Voyager probes were launched in the 1970s, they carried plaques showing the positions of pulsars relative to the Sun, their pulse rates etched as identifiers. The idea was that if anyone found those probes, pulsars would be the universal landmarks to guide them back to our corner of the galaxy. There is also a human fascination with the sound of pulsars. When their radio signals are converted into audio frequencies, they become steady beats, clicks, or hums. Listening to them is eerie and mesmerizing. It is as if the universe itself is drumming in the distance, keeping time in a rhythm that never wavers. These sounds remind us that what we detect as abstract data is in fact the heartbeat of collapsed stars, broadcasting across light years. The dance of pulsars is not only a scientific curiosity, but also a reminder of resilience. Out of the death of massive stars, out of explosions that tear apart stellar bodies, comes something that spins steadily, rhythmically, almost peacefully. Their beams sweep across the universe without regard for who is watching. Yet for us they provide knowledge, inspiration, and even a kind of cosmic companionship. Each pulse we detect is a reminder that far away, a star that once died is still speaking in the only way it can. And as steady as they are, pulsars are not frozen in time. They do evolve, they do change. Their spins gradually slow, their beams weaken, and eventually many fade into silence. But in the span of millions of years, their persistence is remarkable. Some even experience sudden jumps in their spin rate, called glitches, thought to be caused by shifts in their internal structure. These glitches reveal clues about what lies inside them, offering rare glimpses into physics at densities far beyond laboratory reach. So when astronomers call them cosmic lighthouses, it is not just because they sweep beams across space. It is because they guide us, steady and reliable, showing us the way toward understanding the universe. They stand as beacons not of danger, but of rhythm, order, and endurance. They are dead stars that somehow still live, sending their signals with unwavering patience. When you think of speed in the universe, it's natural to picture rockets, planets, or maybe comets streaking across the sky. Even Earth itself feels fast when you remember it's moving around the Sun at about 67,000 miles per hour, while the Sun orbits the centre of the galaxy at hundreds of thousands of miles per hour. But these speeds, impressive as they are, pale in comparison to the dizzying rotation of certain neutron stars. The fastest spinners in the universe are not giant planets or blazing stars, but compact corpses of stars that died long ago, now whirling so rapidly that they complete hundreds of revolutions every second. To begin with, imagine something the size of a city. Picture a sphere about 12 miles across, no larger than a metropolitan skyline, yet containing more mass than our Sun. Now imagine that sphere rotating not once every day, as Earth does, not once every 10 hours, as Jupiter does, but hundreds of times each second. That is the reality of millisecond pulsars, the record holders among neutron stars. These objects spin so quickly that if they had surfaces you could stand on, you would be carried around at speeds approaching a tenth the speed of light. And still, their gravity is strong enough to keep them intact. The fastest known pulsar spins about 716 times per second. That means in the blink of an eye, it has already turned hundreds of times. At such speeds, the outer crust is subjected to enormous centrifugal forces. For any ordinary material, this would be impossible. It would fly apart instantly. But the crust of a neutron star is no ordinary material. It is stronger than steel, supported by nuclear forces and the unimaginable gravity that holds the star together. The balance between rotation and gravity is delicate, but it works, allowing these stars to maintain such incredible speeds for millions or even billions of years. The question naturally arises, how do they get so fast? Most neutron stars are born spinning rapidly after a supernova, but not at millisecond speeds. Over time, they actually lose energy, slowing down gradually as they emit radiation. Yet in certain cases, a neutron star can be spun up again by the influence of a companion star. If the neutron star orbits close to another star, material from the companion can be drawn in, forming an accretion disk around it. As this material spirals inward, it transfers angular momentum to the neutron star, effectively giving it a push. Over millions of years, this process can accelerate the star's rotation until it is spinning hundreds of times each second. This is why many of the fastest pulsars are found in binary systems. The companion acts as a cosmic dance partner, passing energy and momentum to the collapsed star until it becomes one of the fastest spinners in the cosmos. This recycling process is remarkable in itself. It shows how interconnected stars can be, how even in death one can draw life from another. The neutron star, long since collapsed and quiet, is revived into a pulsar by the slow siphoning of matter from its companion. The result is a kind of second life, one defined not by fusion but by rotation. The speeds involved stretch our intuition. Think of a kitchen blender spinning at a few thousand revolutions per minute. Think of a jet engine turbine spinning even faster. Now multiply that by tens of thousands, and imagine that instead of light machinery, it is an object with more mass than the Sun. The fact that such a thing can exist at all is staggering. It pushes our understanding of matter, structure, and physics itself. Astronomers study these millisecond pulsars for more than just their novelty. Their precision makes them invaluable tools. Because they spin so regularly, their pulses arrive at intervals that can be measured with extreme accuracy. Small deviations in these intervals can reveal the presence of orbiting planets, the influence of gravitational waves, or the details of their interactions with companions. In fact, the first exoplanets ever discovered were found around a millisecond pulsar. That may seem strange, planets around the corpse of a star, but it shows how resilient planetary systems can be, surviving even catastrophic explosions. Another remarkable aspect of these fast spinners is their stability. Despite rotating so quickly, they remain steady for extraordinary lengths of time. The forces inside them, though extreme, are balanced. Their immense density gives them rigidity, and their loss of energy through radiation is gradual. They are not fragile things barely holding together, but enduring objects capable of maintaining their speeds for eons. It's also worth considering what limits their rotation. At some point, if a neutron star were spun too fast, it would break apart. The precise limit depends on its mass and structure, but calculations suggest it is around 500 revolutions per second. The fastest observed so far is about half that, so even at their record-breaking speeds, they are not yet at the theoretical edge. Somewhere in the galaxy, perhaps, there may exist one spinning even faster, waiting to be discovered. The environment around these fast pulsars is also fascinating. Their rapid rotation drives magnetic fields of astonishing strength. These fields accelerate particles and produce beams of radiation, just as in slower pulsars, but the frequency and energy of the emissions can be different. The interaction with companion stars can create streams of matter, shock waves, and bursts of energy. In some cases, these pulsars are so active that they ablate or strip away their companions with relentless radiation. Such systems are nicknamed Black Widow pulsars, after spiders that consume their mates. It is a vivid image, but one grounded in real astrophysics. From Earth, what we see is the steady beat of their pulses, arriving with machine-like precision. But behind that steadiness lies an object spinning at unimaginable speed, shaped by gravity, sustained by nuclear forces, and glowing with the energy of its rotation. It is not just a curiosity, but a probe into the nature of matter at its most extreme. Every pulse carries information about the star's structure, its magnetic field, its environment. By listening carefully, astronomers can piece together the secrets of these fastest spinners. In a way, they remind us of balance. They should not exist, yet they do. They spin so quickly that it seems impossible, yet their density allows it. They are remnants of death, yet they live on as clocks and beacons. They show that in the universe, extremes are not only possible but sometimes stable, even enduring. And while their speeds are extraordinary, they are not unique in their essence. They are simply neutron stars pushed to their limit, showing us what happens when gravity, matter and motion are taken as far as they can go without breaking. They are testaments to the resilience of the laws of physics and to the surprises the universe still holds. When people hear about neutron stars, they usually think first about their density or their powerful gravity. Those are indeed staggering, but another remarkable feature lies in their surface. Beneath the swirling beams of radiation and the invisible warping of space-time, a neutron star has a crust so strong it defies comparison to anything we know on Earth. Calling it stronger than steel is not poetic exaggeration. It is a literal understatement. Imagine the surface of a neutron star. It is only a thin shell compared to the whole object, perhaps a kilometre thick out of the 12 or so that make up its diameter. Yet within that shell lies material in states completely unfamiliar to us. At the very top you might find something resembling ordinary atomic nuclei packed into a solid lattice, similar in concept to crystals here on Earth, but far denser. As you descend, the pressure increases, and atoms are squeezed so tightly that their electrons are stripped away, leaving a sea of charged particles surrounding a dense array of nuclei. Deeper still, even those nuclei begin to deform, stretch, and merge into exotic shapes sometimes described as nuclear pasta. Structures of matter squeezed into rods, sheets, and more bizarre geometries by the crushing forces around them. This crust is not fragile. It is not brittle like a rock, nor soft like a metal under heat. It is, according to simulations and calculations, the strongest known material in the universe. To break it would require pressures and stresses unimaginable by earthly standards. Experiments with computer models suggest that the crust could withstand strains 10 billion times greater than steel before breaking. If you tried to dent it with even the largest explosive ever built, it would be like trying to scratch diamond with a feather. The reason for this strength is partly its density. On Earth, even the hardest materials have gaps between atoms. In the neutron star crust, those gaps are minimal. Matter is packed so tightly that the forces binding it together are orders of magnitude stronger. In addition, the gravity above it presses down with unrelenting pressure, reinforcing the structure from the outside as well as within. The result is a surface that could support mountains no more than a few centimetres tall before they collapse under their own weight. And yet those tiny mountains, in terms of mass, would outweigh Everest. This extreme strength has real consequences. For instance, it allows neutron stars to build up stress within their crusts. As the star spins, as its magnetic field twists and shifts, as material accretes from a companion, the crust can deform slightly. Over time, strain accumulates, just as tectonic plates on Earth build up stress before an earthquake. When the crust finally yields, it produces what astronomers call a star quake. The sudden adjustment can release bursts of energy detectable across the galaxy, sometimes as flashes of X-rays or gamma rays. In this way, the strength of the crust doesn't prevent events, it enables them by allowing enormous amounts of stress to build before being released all at once. These starquakes give scientists clues about what lies beneath. By studying the timing and energy of the bursts, astronomers can infer how rigid the crust is, how it responds to pressure, and even what exotic phases of matter might exist in the layers below. In recent years, computer simulations have become more sophisticated, showing how nuclear pasta could form strange structures with incredible mechanical strength. The idea that matter could organise itself into such bizarre configurations, dictated not by chemistry but by nuclear forces, is one of the strangest predictions to come from studying neutron stars. It is also worth thinking about what this crust means for the star's magnetic field. Neutron stars often have magnetic fields trillions of times stronger than Earth's. These fields are anchored in the crust, twisted and shaped by its rigidity. When the crust shifts, the magnetic field lines can snap and reconnect, releasing bursts of radiation. This is particularly true for magnetars, a type of neutron star with especially strong magnetic fields. In those cases, crustal shifts and magnetic activity combine to produce flares so powerful they can briefly outshine entire galaxies. Comparisons to steel help us appreciate the scale, but they hardly do justice to the reality. Steel, the backbone of our industrial world, is prized for its combination of strength and flexibility. Yet in the face of neutron star matter, steel might as well be tissue paper. The difference is not just a factor of 10 or 100, but billions. The crust of a neutron star is a reminder that the laws of physics, when pushed to extremes, create materials beyond anything we can engineer. One of the intriguing questions is how this crust transitions to the interior. As you move downward, neutrons begin to leak out of nuclei, forming a sea of free neutrons mixed with nuclear pasta. This region may behave like a superfluid, flowing without resistance, while the crust above remains solid. The boundary between these layers is not well understood, but it is thought to be crucial in phenomena like pulsar glitches, sudden changes in the star's rotation rate. These glitches suggest that the interior superfluid can momentarily decouple from the crust, then transfer angular momentum back to it, causing a jump in spin. Again, the crust's rigidity plays a role, locking the rotation until stress builds enough to shift. This crust also makes neutron stars surprisingly stable against collapse. Without it, their surfaces might deform more easily, altering their spin or shape. But with such strength, they can maintain nearly perfect spheres, spinning at hundreds of revolutions per second without flying apart. Even the fastest pulsars rely on the strength of the crust to maintain coherence. It is the skeleton that holds the star together against unimaginable forces. Astronomers continue to explore the implications of such a crust. Could it produce gravitational waves detectable from Earth? If the crust has imperfections, mountains or irregularities, however tiny, they could cause the star to radiate gravitational waves as it spins. Detecting those waves could provide direct measurements of crustal strength and structure. Already, detectors like LIGO and Virgo are pushing towards sensitivities where such signals might one day be observed. The crust, silent and invisible to the eye, may leave a fingerprint on the very fabric of space-time. The thought of such strength is both humbling and unsettling. On Earth, we measure progress in terms of the materials we can shape: bronze, iron, steel, carbon fibre. Each advance has allowed new feats of engineering, from bridges to skyscrapers to spacecraft. Yet all of those together are dwarfed by the natural engineering of a neutron star's crust. Nature, indifferent and automatic, has created a material far beyond our reach, born not in a laboratory, but in the collapse of giants. When we picture that surface, we can imagine a place no one will ever walk, a landscape of unimaginable density, crusted with atomic lattices, rippling occasionally with quakes that send bursts of energy across the galaxy. Stronger than steel, stronger than anything else, it endures as the outermost skin of one of the universe's most extreme objects, and just beneath that skin, stranger things still await. When you think about forces in the universe, gravity usually takes centre stage. It shapes planets, sculpts galaxies, and creates black holes. But neutron stars remind us that gravity is only part of the story. Some of them carry another power that rivals even gravity in its ferocity. These are the magnetars, neutron stars with magnetic fields so intense they distort the very space around them. If ordinary neutron stars are remarkable, magnetars are something beyond that. They are the magnetic monsters of the cosmos, their invisible fields stronger than anything else known in nature. To begin imagining them, think about the magnetic field of Earth. It protects us from solar winds, it guides compasses, and it shapes the auroras that ripple in the polar skies. Its strength is measured in a few tenths of a Gauss at the surface, a unit small enough that we rarely consider it outside physics textbooks. A refrigerator magnet is stronger, usually around 50 Gauss. The most powerful magnets built in laboratories can reach tens of thousands of Gauss. Impressive, but still limited. The magnetic field of a neutron star, even an ordinary one, can reach 1 trillion Gauss, and a magnetar, its field can be 1,000 times stronger than that. We're talking about numbers so vast that they almost lose meaning. 10 quadrillion Gauss. What does that even mean in practice? For one thing, such a magnetic field is strong enough to alter the structure of atoms. Normally, electrons orbit nuclei in diffuse clouds, defining the chemical properties of elements. In a magnetar's field, those orbits are squeezed into elongated shapes, changing chemistry itself. Materials would behave in ways completely unfamiliar, their properties dictated not by bonds and lattices but by the overwhelming dominance of magnetism. Even vacuum itself may not behave normally. Quantum effects become important, creating a bizarre environment where light interacts differently with space. If somehow you could stand near one, which, thankfully, you cannot, your very body would not survive. The field would be strong enough to tear electrons from atoms, dismantling molecules instantly. At a distance of 1,000 kilometers, a magnetar could erase the electronic memory of every computer on Earth. That's how far its influence could reach. It is a reminder that in the cosmos, danger does not always come from explosions or impacts. Sometimes it comes from invisible fields stretching silently across space. Magnetars are rare, Out of the hundreds of millions of neutron stars thought to exist in our galaxy, only a few dozen have been identified as magnetars. Their rarity makes them fascinating, and their behaviour makes them unforgettable. They are prone to violent outbursts, sudden flares of X-rays and gamma rays that can release more energy in a fraction of a second than the sun emits in 100,000 years. These flares are thought to be triggered by shifts in their crust, where the enormous stresses of the magnetic field eventually snap and rearrange. When that happens, the energy stored in twisted magnetic lines is released, cascading outward as radiation detectable across the galaxy. One of the most dramatic examples occurred in 2004, when a magnetar called SGR 180620 erupted in a giant flare. The burst was so powerful that it briefly affected Earth's atmosphere from 50,000 light-years away. That's nearly half the diameter of the Milky Way, and yet the event was strong enough to leave a measurable mark here. Had it been only a few light-years away, the consequences for life on Earth would have been catastrophic. Fortunately, magnetars are distant, their fury confined to the far reaches of the galaxy. The physics behind their magnetism is still an open question. The leading idea is that when a neutron star forms, if its core is rotating especially rapidly and convection is strong, it can create a dynamo effect. That dynamo amplifies magnetic fields to enormous strengths, locking them into the star's crust and interior. Over time, those fields may decay, but during the first 10,000 years of a magnetar's life, they dominate its behaviour. This makes magnetars relatively young by neutron star standards, cosmic adolescents still brimming with raw power. What's remarkable is how these fields can interact with their surroundings. In some cases, magnetars are thought to power mysterious bursts of radio waves known as fast radio bursts, or FARBs. These millisecond-long flashes of energy are among the most energetic phenomena in the universe, and although their origins are still debated, magnetars are a leading candidate. If true, it would mean that the restless activity of these magnetic monsters is responsible for signals we can detect across billions of light-years. To put their magnetism in perspective, imagine the most powerful MRI machine in a hospital. It uses a magnetic field of a few tens of thousands of Gauss to produce detailed images of the human body. Step inside, and you can feel the tug on small pieces of metal, though the field is carefully contained. Now imagine a magnet 1 trillion times stronger. In such a field, atoms themselves are distorted. Space is reshaped. Light curves in ways that defy our usual understanding. This is not just magnetism as we know it. It is magnetism elevated to a cosmic force, a fundamental player in the dynamics of stars and galaxies. Even the decay of these magnetic fields has consequences. As the field lines shift and reconnect, they heat the crust of the star, producing persistent X-ray emissions. This makes magnetars visible long after their birth, glowing faintly but steadily in high-energy light. They are beacons, not of visible brightness, but of invisible radiation. Astronomers equipped with X-ray observatories can trace their presence, studying the flickers and flares to piece together the puzzle of their internal workings. There is also a strange elegance to how these fields couple with the star's rotation. As the magnetar spins, its field interacts with the surrounding space, creating currents and winds of particles. These winds can strip away energy, slowing the rotation more quickly than in ordinary pulsars. This means magnetars tend to spin more slowly, with periods of seconds rather than milliseconds. Yet what they lose in speed, they make up for in raw magnetic dominance. Their slower rotation is deceptive, hiding the fact that their fields are storing and releasing energies greater than almost anything else we can observe. The discovery of magnetars also reshaped how we think about neutron stars in general. Before they were identified, bursts of gamma rays detected in the late 20th century puzzled astronomers. Many thought they came from distant galaxies or exotic objects. Only later did the realization dawn that some of these bursts were from magnetars in our own galaxy. That recognition not only solved a mystery but opened a new field of study. Magnetars showed that neutron stars are not all the same. They are diverse, with different personalities shaped by their birth conditions, their rotation, and their magnetism. For us, magnetars are distant curiosities. None lie close enough to pose a threat, yet their existence challenges our understanding of physics. They force us to ask how matter behaves under the combined influence of gravity and magnetism at such extremes. They test the limits of quantum electrodynamics, the theory of how light and matter interact. And they provide laboratories for processes that cannot be recreated anywhere else. The phrase magnetic monsters is fitting, but not because they are evil or hostile. It is because their magnetism is monstrous in scale, dwarfing anything else in nature. They remind us that the universe contains not only crushing gravity and blazing light, but also invisible forces stretched to their limits. They are stars whose defining feature is not their mass or their spin, but their magnetic grip on space itself. And as with everything about neutron stars, they are not an ending point. Their fields decay, their flares fade, and eventually they may settle into quieter forms. But while they rage, they are among the most dramatic actors in the cosmic play. Each flare, each burst, each distortion of space is a signal of what happens when the universe pushes magnetism to its maximum. We usually think of stars as silent. From our vantage point they shine without a sound, their light crossing space in pure silence, untouched by air or atmosphere. Yet neutron stars remind us that silence is only an illusion of distance. These objects, dense beyond comprehension, can shake, rattle and hum in ways that are more musical than anything we might expect. They sing not with voices but with vibrations, quakes and resonances that echo through their dense crusts and magnetic fields. Astronomers cannot hear them directly in the sense we hear a violin or a drum, but their instruments can translate these stellar songs into data, sometimes even into sound we can listen to. And when they do, we find that dead stars can still sing. The origin of this music lies in the crust and the magnetic fields of neutron stars. As we have seen, their outer layers are stronger than steel, rigid enough to store incredible stresses. But no material, however strong, can withstand pressure indefinitely. Over time, as the star spins, as its interior superfluid shifts, as its magnetic field twists, the crust accumulates strain. When it can no longer hold, it cracks in sudden adjustments called starquakes. These events are like earthquakes on Earth, but on a scale far greater. The crust snaps, vibrations ripple outward, and energy is released as bursts of radiation. The neutron star trembles, and the tremors ring through it like the strike of a bell. Those vibrations can couple with the magnetic field, creating oscillations detectable from far away. In some magnetar flares, astronomers have observed quasi-periodic oscillations, repeating signals in the X-ray light that fade gradually but carry a distinctive rhythm. These oscillations are thought to be the resonant modes of the star itself, the way it naturally vibrates after being struck by a quake. Imagine hitting a tuning fork. The metal rings with a pure tone until it fades. A neutron star does the same, but its tone is encoded in light and magnetism instead of sound. This is why some astronomers speak of neutron stars as singing. Their quakes and vibrations create signals that are not random, but patterned, resonant, structured. Each oscillation is a note, each flare a chord. Together they form a music unlike any other, the music of matter at nuclear density. And while it is not audible to human ears without translation, it is no less real. The idea of stellar music is not new. Even ordinary stars have oscillations, subtle ripples that astronomers study under the field of astroseismology. Our sun hums with waves that resonate through its interior, and by studying those waves scientists learn about its structure. But neutron stars elevate this idea to an extreme. Their density, their rigidity, their magnetism all combine to create vibrations of extraordinary frequency and power. These are not the gentle oscillations of a living star, but the violent ringing of a collapsed one. To appreciate what this means, think again about the strength of the crust. When it breaks, the energy released is immense. Starquakes can unleash bursts equivalent to the energy our Sun produces in 100,000 years. That energy does not just vanish into space. Some of it stays in the star, setting it ringing like a struck drum. These vibrations, though fleeting, carry information about the star's interior. By studying them, astronomers can probe layers that are otherwise hidden. It is like listening to the echoes in a cave to learn its shape. In 1998, a giant flare from the magnetar SGR 1900 + 4000 provided one of the first clear examples. The X-ray light flickered with repeating patterns, frequencies that matched what would be expected from seismic vibrations in the crust. Later events from other magnetars showed similar signatures, confirming that neutron stars really do ring when they quake. Each frequency corresponds to a mode of vibration, and by cataloguing them, astronomers can build a picture of the star's structure. In this way, neutron star seismology becomes possible, just as seismology on Earth reveals the layers beneath our feet. What's more, these vibrations may not be confined to the crust alone. They may couple with the superfluid interior, creating complex patterns that reflect the interplay of solid and liquid phases inside. Some models suggest that vortex lines in the superfluid can pin to the crust, storing angular momentum, then unpinning suddenly in glitches. These events may also excite oscillations, adding to the star's repertoire of sounds. It is a symphony not of instruments, but of quantum states, nuclear forces, and gravitational grip. When these oscillations are converted into audible frequencies for human listening, the result is eerie. Astronomers have taken pulsar signals, stretched or compressed them, and made recordings where the beat of a neutron star becomes a steady click or hum. Add the oscillations from flares, and you get tones and patterns that resemble percussion, sometimes even melodies. It is not music in the human sense, but it is rhythm, it is tone, it is vibration turned into sound. To listen to it is to be reminded that the universe is not silent at all. It is filled with vibrations waiting to be heard. The cultural resonance of this idea is powerful. People have always associated music with the heavens, from the ancient concept of the music of the spheres to modern compositions inspired by astronomical data. Neutron stars bring that metaphor into literal reality. They do sing in their own way, and by listening we learn. Their music is harsh, violent, sometimes catastrophic, but also structured, ordered, beautiful in its own alien way. And beyond beauty, there is science. These stellar songs tell us about the physics of matter under conditions we cannot replicate. They tell us how rigid the crust is, how strong the magnetic field is, how the superfluid interior behaves. They test theories of quantum chromodynamics, the physics of quarks and gluons, because the vibrations depend on whether neutrons remain intact or dissolve into quark matter. Each oscillation is a clue, each note a data point. Starquakes also hint at the lives of these stars. The frequency of quakes, the energy of flares, the patterns of oscillations all reveal whether a magnetar is young and restless or older and quieter. They show how its magnetic field evolves, how its crust adjusts to stress, how it slowly spends its stored energy. In this way, listening to their music is also listening to their biography, the unfolding of their lives after death. The image of a star singing may sound fanciful, but it is grounded in hard measurement. Satellites detect the flickers of X-rays, instruments record the timing of pulses, computers analyse the frequencies, the data is real, the patterns undeniable. What we call music is just one way of framing it, but the resonance is genuine as the ringing of a bell or the vibration of a string. The difference is scale, and the difference is violence. As we reflect on this, it is humbling to realise how limited our senses are. We look up at the night sky and see calm points of light. Yet behind that calm, neutron stars quake and sing, their vibrations shaking space and radiating energy. We are deaf to it without our instruments, but once we translate it, we realise that the universe is filled with music, some soft, some violent, some beyond anything our ears evolved to hear. And these songs are not fleeting curiosities. They carry implications for the search for gravitational waves. Just as oscillations in the crust produce X-ray flickers, they may also send ripples through space-time. If detectors become sensitive enough, they could capture these waves, adding another instrument to the cosmic orchestra, listening not just with light, but with gravity itself, to the ringing of neutron stars. In the end, whether we call it singing, ringing, or oscillating, the message is the same. Neutron stars are not silent corpses. They are active, vibrant, sometimes explosive. Their crusts crack, their fields snap, their interiors shift, and each movement leaves a mark. They remind us that death in the universe is not quiet but resonant, continuing long after the visible light has gone out. And just as one quake fades, another builds. Just as one vibration dies down, new stresses accumulate. The music never truly stops. It shifts, it changes, it evolves. And for those with ears to hear, it tells the story of matter itself pushed to the edge of possibility. The idea of a quake on a star feels strange at first. Here on Earth, we understand earthquakes as the grinding of tectonic plates, the release of stresses built up along faults, the shifting of rock beneath our feet. We know the sound, the vibration, the chaos. But what does it mean when a star quakes? A neutron star is not made of rock in the usual sense, nor does it have plates that drift across a molten mantle. And yet these stars experience their own version of seismic activity, sudden shifts in their rigid crust that unleash bursts of energy powerful enough to be felt across light years. These are the star quakes, and with them come bursts of radiation that puzzle and intrigue astronomers even today. To begin to understand the mystery, it helps to return to the crust. That thin outer shell of a neutron star, only a kilometre thick, is unimaginably strong. But it is not unyielding. As the star spins, as its interior changes, as its magnetic fields twist and writhe, stresses accumulate in the crust. It is as though the surface is being bent, pulled and strained by forces both internal and external. At some point, the crust can no longer bear the load. It cracks. That cracking is not gentle. It is sudden, catastrophic, and energetic on a scale beyond imagination. The release of energy is what we call a starquake. The effects ripple outward instantly. Vibrations travel through the dense matter, ringing the star like a struck gong. The magnetic field anchored in the crust is jolted and shifts suddenly, sometimes snapping and reconnecting in new configurations. When that happens, vast amounts of energy are released into space as bursts of radiation, often in the X-ray or gamma-ray part of the spectrum. To an observer with the right instruments, it appears as a sudden flare, a bright flash from an otherwise faint or even invisible source. The puzzle lies in the details. Not every neutron star produces these bursts. Even those that do can vary dramatically, some emitting small, frequent flares, others releasing rare but gigantic eruptions. The underlying trigger is still debated. Is it purely the mechanical strain in the crust? Is it the twisting of magnetic fields storing energy until they break? Or is it some interaction between the two, a dance of forces so intertwined that they cannot be separated? The truth is likely all of these, but the exact proportions remain uncertain. One of the most famous cases that revealed the nature of starquakes came in 1979. This sudden burst of gamma rays lit up detectors in orbit around Earth, so intense that at first scientists thought it came from a nuclear detonation nearby, but calculations quickly showed it originated far away, from a source in our galaxy. That event, traced to a magnetar, was the first clear indication that neutron stars could produce bursts of such magnitude. Since then, dozens of similar events have been catalogued, ranging from brief flickers to colossal outbursts that rival the energy output of entire galaxies. The mystery deepens when we examine the rhythms hidden within these bursts. In some cases, the light flickers with repeating patterns, oscillations that suggest the star itself is vibrating after the quake. These quasi-periodic oscillations give astronomers a way to probe the interior of neutron stars. They act as seismological fingerprints, clues to the density, composition and structure of the crust and core. But interpreting them is not simple. The physics of matter at such densities is still not fully understood. Competing theories suggest everything from nuclear pasta phases to superfluid vortices, each leaving different imprints on the vibrations. Adding to the enigma are the smaller bursts, sometimes seen as brief flashes in X-rays, lasting only milliseconds. These may represent minor cracks in the crust, small shifts that relieve localized stress. But even these minor events can release as much energy as a massive earthquake on Earth. The scale of neutron star physics makes our own planet's geology seem almost delicate. Another layer of mystery comes from the connection between starquakes and fast radio bursts. These fast radio bursts, or RBs, are millisecond-long flashes of radio energy that originate from outside our galaxy, perhaps from billions of light-years away. Their origin has been debated fiercely since their discovery. Some theories link them to magnetar activity, suggesting that starquakes and magnetic reconnections could produce bursts of radio energy strong enough to travel across the cosmos. In 2020, for the first time, astronomers detected a fast radio burst from within our own galaxy, and it was traced to a magnetar. This provided compelling evidence that at least some FRBs are indeed tied to starquakes and bursts on neutron stars. The implications are staggering. It means that events happening on the surface of a collapsed star, only a dozen miles wide, can send signals powerful enough to be detected across billions of light-years. The cracking of a crust, the snapping of magnetic lines, the sudden rearrangement of energy, these things ripple outward not just locally but cosmically. It shows the scale of connection in the universe, where even the smallest fractures on the most compact stars can leave marks across intergalactic space. Yet despite these insights, many questions remain. What controls the frequency of starquakes? Why do some magnetars erupt in giant flares while others remain comparatively quiet? How exactly does the magnetic field interact with the crust? Do these events alter the star permanently, changing its spin or magnetic configuration, or are they transient, fading quickly without long-term consequences? Astronomers continue to gather data, but the answers are elusive. Part of the challenge is simply the unpredictability of these events. Starquakes and bursts happen without warning, and often the instruments needed to observe them are not pointing in the right direction at the right time. Unlike pulsars, whose regular pulses can be predicted and tracked, starquakes are chaotic. They are sudden eruptions of energy that defy forecasting. When they do occur, astronomers scramble to capture as much data as possible, coordinating satellites and ground-based observatories to catch the fading echoes. The scale of their power also challenges our models. When a giant flare is released, the energy output can be so high that it challenges our understanding of how the crust and magnetic field could store it in the first place. Some models propose that the energy is not confined to the crust alone, but extends deep into the star's interior, where superfluid motions or quark matter phases may also play a role. If so, then starquakes are not just surface events but windows into the deepest mysteries of matter itself. For those of us listening from afar, these bursts are reminders that stars do not simply fade quietly into the night after death. They continue to live dynamic lives, cracking, quaking, flaring and singing. Each burst is a flare of activity, a signal that something unimaginable has shifted beneath the surface. They are mysteries not just because we do not fully understand them, but because they reveal how much more there is to learn about the most extreme objects in the cosmos. And as the story of starquakes and bursts unfolds, we find that their consequences are not confined to the stars themselves. Their energy travels outward, influencing nearby space, sometimes stripping companions of material, sometimes driving shockwaves through surrounding nebulae. Their radiation can alter distant atmospheres. Their vibrations can ripple through space-time. Their signals can become tools for measuring the universe. They are not isolated curiosities, but actors in a broader drama, shaping the galaxy in subtle ways. In this sense, the mystery of starquakes and bursts is not a single puzzle to be solved, but a field of inquiry that will likely last for decades. Each new burst adds a piece, each oscillation a clue, each fast radio burst a hint of a larger pattern. The more we observe, the deeper the mystery becomes, pulling us further into questions of matter, magnetism, and the restless lives of collapsed stars. And all the while, as these mysteries accumulate, the stars continue to quake. Somewhere right now, unseen and unnoticed, a magnetar's crust may be cracking, its magnetic field snapping, its radiation bursting outward. We may never detect it, but the event is real, another note in the vast cosmic score. The mystery remains, not because the universe hides it, but because we are only beginning to learn how to listen. When two neutron stars drift through space alone, they are already extreme enough. Each is the compressed remnant of a massive star, dense, magnetic, spinning, holding within itself the physics of matter under crushing conditions. But sometimes they are not alone. Sometimes they are born together, the remnants of a binary system, or drawn together by gravity over time. When that happens, when two neutron stars orbit each other in a cosmic dance, the story becomes even more astonishing. Their mutual pull creates spirals of energy, their orbit shrinks, and eventually they collide. These collisions are among the most violent and spectacular events the universe can produce, shaking the fabric of space-time itself. To picture this, imagine two spheres, each no larger than a city, yet each weighing more than our sun. They circle one another in silence, separated at first by tens of thousands of miles. With every orbit they emit gravitational waves, ripples in the very structure of space-time. These waves carry away energy, and as energy is lost, the stars draw closer. Their orbits shrink, their speed increases, and the cycle accelerates. What begins as a slow waltz becomes a furious spin, until finally the two bodies spiral together and merge. The final moments happen quickly. In the last few seconds before collision, the stars circle each other hundreds of times per second, moving at a significant fraction of the speed of light. The forces involved are indescribable. Their crusts stretch and distort, tidal forces tearing at them, matter flung outward in arcs. When they finally meet, the collision releases more energy than anything else short of the Big Bang itself. Light, heat, gravitational waves and heavy elements are cast into the galaxy in a single overwhelming moment. We know this not just in theory but in observation. In 2017, detectors on Earth recorded a gravitational wave signal unlike any seen before. It lasted longer than the brief chirps of black hole collisions, showing a steady chirp of increasing frequency and amplitude as two neutron stars spiraled together. At almost the same time, telescopes around the world detected bursts of gamma rays, X-rays, and visible light from the same region of sky. For the first time, astronomers had observed both gravitational and electromagnetic signals from a single cosmic event. It was the merger of two neutron stars, confirmed beyond doubt. That event, catalogued as GW 170817, was a watershed moment in astronomy. It confirmed theories about how gravitational waves behave. It provided direct evidence for the creation of heavy elements in neutron star collisions, and it opened a new era of multi-messenger astronomy. For centuries, we observed the universe only in light. With this event, we observed it in both light and gravity. The cosmos had spoken in two voices at once, and the message was clear. Collisions of neutron stars are not just violent, they are creative. One of the most important outcomes of these collisions is the production of heavy elements. Gold, platinum, uranium, and many others cannot be formed in ordinary stars. They require environments with extreme densities of neutrons, where atomic nuclei can rapidly capture them. This process, known as the R process, occurs during neutron star mergers. In the aftermath of GW 177 astronomers studied the light from the explosion and found the spectral fingerprints of these heavy elements. It was the proof long sought. Much of the gold in the universe, including the gold in jewellery and electronics here on Earth, was born in the collision of neutron stars. Every ring, every coin, every circuit carries within it the memory of a cosmic catastrophe. The collisions also reveal something about the nature of neutron stars themselves. By studying the gravitational wave signal, scientists can infer how the stars deformed as they spiraled together. This tells us about the stiffness of neutron star matter, the so-called equation of state that describes how dense matter behaves. It is an open question in physics, one that laboratories cannot answer. Only by listening to the vibrations of colliding neutron stars can we glimpse these secrets. And yet, for all the drama of the collisions, they are not rare freak events. In a galaxy of hundreds of billions of stars, binary systems are common. Some of those binaries contain massive stars, and when both explode as supernovae, the remnants can remain gravitationally bound. Over millions or billions of years, they spiral inward until they collide. Across the observable universe, neutron star mergers are happening all the time, each one a burst of light and gravity, each one a forge of elements, each one a ripple through space-time that we may or may not detect, depending on its distance and orientation. The scale of these events is difficult to hold in the mind. The final collision may last only seconds, but the after-effects linger for weeks or months. The explosion, called a kilonova, shines brightly in visible light, its colour shifting from blue to red as the ejector expands and cools. In infrared light, the glow can persist even longer, revealing the formation of heavy elements. These kilonovae are now a focus of study, as they allow astronomers to directly observe the creation of the building blocks of planets and life. It is worth pausing here to think about what it means for a collision to shake the cosmos. Gravitational waves are not sound in the usual sense, but they are vibrations of space itself. When two neutron stars merge, they send out ripples that travel across the universe, stretching and squeezing space by tiny amounts. By the time they reach Earth, those ripples are smaller than the width of a proton, and yet with delicate instruments like LIGO and Virgo, we can detect them. We can feel, in a sense, the trembling of space caused by stars colliding hundreds of millions of light years away. This connection between the violent and the delicate is one of the wonders of modern science. Immense explosions shake the universe, and sensitive detectors here on Earth, using lasers and mirrors, record the faintest echoes. It is like hearing the footsteps of giants by watching ripples in a pond. These ripples confirm Einstein's theory of general relativity. They reveal the lives of stars, and they connect us directly to events far beyond our reach. Collisions of neutron stars also raise questions about what happens in the aftermath. Does the merger produce a black hole immediately, as the mass collapses beyond the neutron star limit? Or can it produce a hypermassive neutron star, briefly stable due to rapid rotation and thermal pressure, before collapsing later? The details depend on the masses involved and the equation of state. Observing these events helps constrain these possibilities, narrowing down the range of what matter can do at the highest densities. Another intriguing aspect is the potential for such collisions to power short gamma-ray bursts. For decades, astronomers observed bursts of gamma rays lasting less than 2 seconds, but their origin was uncertain. Neutron star mergers now provide the leading explanation. The merging cores may form a black hole surrounded by a disk of hot material, which launches jets of particles moving at nearly the speed of light. If one of these jets points toward Earth, we see a short gamma ray burst. The connection was confirmed with GW 170817, when a gamma-ray burst was detected just after the gravitational wave signal. This link solved a long-standing mystery, showing once again how neutron stars influence the broader cosmos. It is almost unsettling to think about how much of what we value comes from these violent collisions. Gold, platinum, uranium, even rare earth elements, all of them owe their existence to neutron star mergers. The same event that produces a flash of light visible across galaxies also produces the materials we mine, shape, and carry with us. The jewellery on a hand, the circuitry in a phone, the fuel in a reactor, all are legacies of stars colliding long before Earth even formed. Our lives are interwoven with these collisions in ways we rarely recognise, and even as we marvel at the beauty and power of these events, we must also acknowledge their danger. Were such a collision to happen close to Earth, within a few tens of light years, the radiation could strip our atmosphere and sterilise the planet. Thankfully, such events are rare in our neighbourhood. Most occur at safe distances, far enough that their only effect on us is inspiration and knowledge. But the possibility underscores the dual nature of the cosmos, creative and destructive, beautiful and dangerous, often in the same moment. The collisions that shake the cosmos are not merely astronomical curiosities. They are central to the story of the universe. They shape galaxies, they create elements, they confirm fundamental physics, and they provide signals that stretch across time and space. Each one is both an ending and a beginning, the death of stars and the birth of new matter. They are reminders that even in destruction, the universe finds ways to create. And as we consider their place in the larger story, it is natural to wonder what comes next. After the collision, after the kilonova fades, after the gravitational waves pass, what remains? Sometimes it is a black hole, sometimes a remnant neutron star, sometimes a magnetar born anew. The cycle continues, the cosmos reshaping itself again and again through the collisions of its most compact objects. When you look at a piece of gold, it feels permanent. Its colour does not tarnish, it resists corrosion, it carries a weight that seems symbolic as much as physical. For thousands of years, people have valued it for beauty, for rarity, for its resistance to time. It has been shaped into crowns, coins, jewellery and circuits, crossing from ancient empires into modern technology. And yet, for all its permanence in human hands, gold's story is one of impermanence and violence on cosmic scales. Every atom of gold on Earth was forged in fire, not the fire of ordinary stars, but the extraordinary explosions and collisions of neutron stars. It is a material born in death, a treasure pulled from the grave of giants. The mystery of gold's origin puzzled scientists for decades. We knew that stars fuse hydrogen into helium, helium into carbon, and in successive stages build heavier elements. But fusion stops at iron. Beyond iron, energy is not released but consumed in fusion reactions. That means the heavy elements must come from somewhere else. For a long time, supernovae were the favoured explanation. The collapse of massive stars seemed violent enough to forge gold, platinum, uranium, and other heavy elements. But calculation showed problems. Supernovae could not account for the observed abundance of these elements. Something else had to be contributing. The answer came with the study of neutron star collisions. In these events, enormous amounts of neutron-rich matter are ejected into space. This environment is perfect for the rapid neutron capture process, known as the R process. In the R process, atomic nuclei capture neutrons at such a furious rate that they build up into heavy, unstable isotopes. These isotopes then decay into stable forms, creating gold, platinum, and countless other heavy elements. The conditions in a neutron star merger, high density, high neutron fleas, high energy, are exactly what the R process requires. It is nature's most efficient forge for the heaviest treasures of the periodic table. The confirmation came with GW1 7, the first observed neutron star collision with both gravitational waves and light. As telescopes studied the aftermath, they detected the telltale glow of heavy elements forming. The kilonova's light shifted from blue to red as the ejector cooled, consistent with the production of gold and platinum. It was the first direct evidence that such mergers are the cosmic forges of the elements we hold so dear. Consider what this means for the world around you. The ring on a finger, the fillings in teeth, the circuits in electronics, all trace back to the death throes of neutron stars. Billions of years ago, long before Earth formed, collisions scattered these elements into the galaxy. They drifted in interstellar clouds, mixed with gas and dust, and eventually became part of the solar system. Without those collisions, Earth would be a poorer place, missing many of the elements essential for technology and life. It's almost unsettling to realise that something so beautiful is born from such violence. The calm gleam of gold masks a history of explosions that shook galaxies. Platinum in jewellery or uranium in reactors comes from the same processes. Even the rare earth elements used in electronics, vital for communication and computing, have their origins in these violent events. The technology you may be using right now to listen to this story depends, at least in part, on neutron star collisions, and it is not just gold. The R process produces a wide array of elements: silver, thorium, neodymium, europium, and many more. Each has its place in the periodic table, and each plays a role in chemistry, geology, and biology. Our bones, our blood, our tools, our art, all are enriched by the products of stellar graves. To study the periodic table is, in a way, to study the remnants of neutron stars. Astronomers estimate that a single neutron star merger can produce tens of Earth masses of gold. Imagine that. Enough gold to cover the surface of our planet in a layer several feet thick. Of course, it is scattered across space, diluted into interstellar clouds, spread thinly over light years, but the total quantity is staggering. It reminds us that rarity on Earth is not the same as rarity in the universe. Gold is scarce here because of how it was distributed, not because it is intrinsically rare. Out there, in the cosmic scale, it has been forged in staggering amounts. This perspective changes how we think about value. For humanity, gold has been the symbol of wealth, the standard of currency, the measure of riches. But to the universe, it is simply one more product of physics, born in moments of destruction, scattered like seeds into the galaxy. Its beauty to us is an accident, a coincidence of colour and chemistry. To the cosmos, it is no more or less significant than any other element. Its story, though, connects us directly to neutron stars, making every piece of gold a relic of stellar death. The process by which it forms is still being studied in detail. When two neutron stars collide, tidal forces strip matter from their surfaces, flinging it outward in streams and clouds. Some of this matter escapes at nearly a third the speed of light. In the chaos, neutrons flood into atomic nuclei, building them up rapidly. The decay of these nuclei releases energy, heating the ejector and producing the kilonova's glow. This light carries the signature of the elements being formed, allowing astronomers to detect them even from hundreds of millions of light years away. It is remarkable that we can look at the faint glow of an explosion and know that within it, gold is being born. The grave of neutron stars is also a cradle. Their death creates the building blocks for new worlds. Without them, the universe would be a simpler place, filled mostly with hydrogen and helium, with small traces of carbon, oxygen and nitrogen. Life as we know it would be impossible. Planets would lack the diversity of elements needed for rocks, oceans, atmospheres, and biology. The richness of the universe, its complexity and its beauty, is due in no small part to the R process in neutron star collisions. It also raises questions about history. How many such collisions happened before the solar system formed? Where in the galaxy did they occur? How far did the ejector travel before becoming part of the cloud that condensed into the sun and planets? These are not easy questions, but they remind us that our own story is inseparable from the story of stars. The gold in human hands today is not just a metal. It is a fossil, billions of years old, carrying within it the memory of neutron stars that lived, died, and collided long before Earth existed. And the story continues. Even now, somewhere in the universe, neutron stars are colliding. Each event is forging new gold, new platinum, new uranium, scattering them into space. In time, those elements may become part of new planets, new civilizations, new stories. The cycle of creation from destruction never ends. When you think of gold in this way, it becomes more than a symbol of wealth. It becomes a symbol of connection, a connection between human history and cosmic history, between the jewellery on a wrist and the most violent events in the cosmos. It is a reminder that we are not separate from the universe, but part of it, carrying its legacy in our hands, our tools, our very bodies. When we look at the sky, we see only part of the story. Our eyes are tuned to a narrow band of light, the small slice of the electromagnetic spectrum we call visible. It is enough for daily life, enough to see colours and shapes, enough to read the stars as twinkling points in the night. But stars, galaxies, and the cosmos at large emit far more than what our eyes can catch. They shine in radio waves, in infrared, in ultraviolet, and, most dramatically, in X-rays and gamma rays. These high-energy forms of light reveal a universe far more violent, more restless, and more extreme than the calm sky suggests. And neutron stars, especially, are among the brightest sources of this invisible glow. X-rays and gamma rays are cousins of visible light, but with much shorter wavelengths and far higher energy. They do not behave gently. X-rays can penetrate flesh, which is why they're used in medical imaging, while gamma rays can disrupt DNA and strip electrons from atoms. On Earth, we shield ourselves from them because they are harmful in excess. In the cosmos, however, they are signatures of some of the most energetic processes in existence. Wherever matter is heated to millions of degrees, wherever particles are accelerated to near the speed of light, wherever magnetic fields snap and reconnect, there you will find X-rays and gamma rays. Neutron stars are almost perfect factories for producing them. Their gravity pulls in matter from their surroundings, especially if they have a companion star. Gas spirals inward, forming an accretion disk that glows in X-rays as it heats up. Close to the surface, particles collide violently, releasing radiation far beyond the visible. In pulsars, beams of particles accelerated by magnetic fields emit X-rays and gamma rays as they sweep across space. In magnetars, bursts and flares unleash torrents of high-energy photons, lighting up detectors on Earth even from thousands of light-years away. For astronomers, this invisible glow is not just a byproduct. It is a window into the hidden workings of neutron stars. Visible light tells us little about these compact objects, since they are so small and faint compared to normal stars. But X-rays and gamma rays cut through the darkness, announcing their presence loudly. Satellites like Chandra, XMM Newton, Fermi and NISA orbit above Earth's atmosphere, which would otherwise block most of this radiation, and they listen to the sky in these high-energy bands. What they record are bursts, pulses and persistent emissions that trace the behaviour of neutron stars in exquisite detail. Consider an accreting neutron star in a binary system. Its companion, perhaps a normal Sun-like star, loses gas to the neutron star's gravity. That gas forms a disk, spiralling inward faster and faster. As it nears the surface, it reaches temperatures of millions of degrees. The result is a steady glow of X-rays, modulated by the star's spin and the geometry of the disk. From these X-rays, astronomers can measure the star's rotation, its magnetic field, even its surface composition. The invisible glow becomes a diagnostic tool, turning destructive radiation into a source of knowledge. Then there are the bursts. Some neutron stars accumulate matter on their surfaces until it ignites in thermonuclear explosions. These Type 1 X-ray bursts last seconds to minutes, releasing as much energy as our Sun emits in days. They are sudden, fierce, and repetitive, providing laboratories for studying nuclear reactions under conditions impossible to replicate on Earth. Each burst is a reminder that even a dead star can flare with nuclear fire if fed by a companion. Magnetars produce even stranger high-energy displays. Their flares can flood detectors with gamma rays, overwhelming instruments designed to capture distant explosions. These giant flares are so bright that for a moment they can rival gamma-ray bursts from other galaxies. The difference is that magnetar flares come from within our own Milky Way, reminding us that these dangerous events are not confined to distant reaches but can occur relatively nearby. Gamma rays from neutron stars also interact with their surroundings. When fast particles are accelerated in pulsar winds, they can collide with interstellar gas, producing secondary radiation. These interactions create nebulae glowing in X-rays and gamma rays, such as the Crab Nebula, where the pulsar at the centre powers a vast cloud of radiation. The nebula shines across the spectrum, but its high-energy emissions are among the most striking, showing us how a single neutron star can energize a region of space dozens of light-years across. This invisible glow also carries timing information. Pulses of X-rays from pulsars arrive with the same precision as radio pulses, sometimes even more cleanly. By analysing these pulses, astronomers can probe the interiors of neutron stars, measuring their rotation rates, their glitches, their changes over time. X-rays reveal how matter flows, how crusts quake, how magnetic fields shift. They are in many ways the voice of neutron stars, broadcasting in a frequency our eyes cannot see, but our instruments can translate. There is also a practical reason why X-rays and gamma rays matter. They show us the extremes of physics. High-energy radiation comes only from the most energetic processes, the places where matter and energy are pushed to their limits. By studying them, we test theories of nuclear physics, quantum electrodynamics, and general relativity. Neutron stars become not just astronomical curiosities, but laboratories for fundamental science. Their invisible glow, the data stream that guides us. The danger of such radiation cannot be ignored, of course. Were a magnetar flare to occur close to Earth, the gamma rays could strip our atmosphere, altering climate and chemistry catastrophically. Thankfully, no magnetar lies near enough to pose that risk. But the possibility underscores the power of these objects. They may be distant, but their light reminds us of the thin line between safety and destruction in the cosmos. Still, the glow is not something to fear at a distance. It is something to marvel at, something to study, something to use as a guide. Astronomers have even used X-ray emissions from pulsars as navigation tools, their regularity serving as cosmic lighthouses for spacecraft. Just as sailors once steered by visible stars, future explorers may steer by the invisible glow of neutron stars, charting courses across the galaxy with pulses of high-energy light. What is striking is how invisible this glow is to our senses. We can look up at the night sky and see nothing unusual. The neutron stars, the pulsars, the magnetars, they do not stand out to the naked eye. Yet with the right instruments, the sky comes alive with bursts and flashes, with steady hums of X-rays, with sudden eruptions of gamma rays. It is like discovering a hidden layer of reality, one that was always there but out of reach until technology revealed it. This hidden universe is immense. Gamma ray bursts, for example, are some of the brightest explosions known, yet they are invisible to our eyes. The same is true for many neutron star phenomena. Without detectors above Earth's atmosphere, we would never know they exist. Our picture of the cosmos would be incomplete, missing the most energetic chapters. The invisible glow expands that picture, reminding us that our senses capture only a fraction of reality. And this glow is not constant. It flickers, it bursts, it fades, it shifts. Each variation tells a story about what is happening on and around the neutron star. Sometimes it is the slow accretion of matter. Sometimes it is the sudden cracking of a crust. Sometimes it is the catastrophic merger of two stars. Each has its signature, its light curve, its spectrum. Together they weave a tapestry of high-energy astrophysics, rich with clues about how matter behaves under the most extreme conditions. So when we think about neutron stars, we must think not only of their density, their spin, their magnetism, but also of their invisible glow. It is the glow that announces them across light years, that gives us access to their secrets, that links our detectors to their surfaces. It is a glow beyond sight, but not beyond comprehension. A glow that reveals the restless, violent and fascinating lives of these collapsed stars. And as one glow fades, another begins elsewhere. The universe is never silent, never still. The invisible light is always there, pulsing, bursting, reminding us that the cosmos holds far more than meets the eye. Time is something we usually take for granted. We measure it with clocks, we feel it in our routines, we notice it in the changes of seasons and in the aging of faces. It seems steady, impartial, and universal. A second is a second everywhere, or so intuition tells us. But the universe is not bound to intuition. Near the most extreme objects, time itself behaves differently. Neutron stars, with their crushing gravity, bend not just space but time. Around them, seconds stretch, minutes distort, and the familiar flow of time becomes strange. To understand why, it helps to think about gravity not as a force in the traditional sense, but as the warping of space-time. This was Einstein's great insight. Mass bends the fabric of space-time, and objects move along the curves. On Earth, the effect is subtle. Time at sea level runs slightly slower than time at the top of a mountain, though the difference is only billionths of a second per year. You never notice it, but satellites and GPS systems must account for it. Without correction, navigation would drift hopelessly off course. That small shift is the everyday proof that time and gravity are intertwined. Now scale that difference up to a neutron star. A neutron star contains more mass than the Sun, but squeezed into a sphere just a dozen miles across. The curvature of space-time is so extreme that time itself runs significantly slower near the surface than it does farther away. A clock sitting on the star would tick slowly compared to a clock in orbit, and both would lag behind clocks here on Earth. If you could stand safely on a neutron star, which you cannot, your heartbeat would feel the same to you, but someone watching from a distance would see it slowed, stretched out in time. This phenomenon is called gravitational time dilation. It means that the deeper you are in a gravitational well, the slower time passes relative to the outside universe. For neutron stars, this effect is profound. In some cases, a few hours near the surface could equal days or weeks farther away. Time is not universal here. It is local, dependent on the strength of gravity around you. The strange thing is that from your own perspective, nothing feels unusual. If you were near a neutron star, your watch would tick normally. Your thoughts would flow at the same pace. Your movements would feel natural. It is only in comparison with the outside world that the difference appears. Someone far from the neutron star would see you slowed, as if trapped in a kind of cosmic molasses. Conversely, if you could look outward, the universe beyond would seem to race ahead, its clock spinning faster, its processes unfolding at a quicker pace. The flow of time itself depends on where you stand. This relativity of time has been tested in many ways on Earth and in orbit. Experiments with precise atomic clocks on airplanes, rockets and satellites confirm it. The predictions match reality to extraordinary precision. Around neutron stars, those same equations describe a much more dramatic effect. It is not speculation, but the natural extension of physics we already know to be true. Consider what this means for light leaving a neutron star. photons emitted from the surface must climb out of the deep gravitational well. As they do, they lose energy, shifting to longer wavelengths. This is called gravitational redshift. From a distance, the light appears dimmer and redder than it would if there were no gravity. In a sense, even light itself feels the slowing of time. Its frequency is stretched, its rhythm altered by the warped flow of seconds near the star. The consequences of this strange time flow extend beyond thought experiments. They influence how neutron stars are observed and understood. The timing of pulsar signals, the spectra of X-ray emissions, the modelling of collisions, all must account for relativity. Without considering time dilation, our interpretations would be skewed. These stars are not just dense matter, they are laboratories for testing how space-time itself behaves under pressure. It is tempting to imagine what it would feel like to experience such time distortion directly. Science fiction often plays with the idea. Astronauts who spend hours near a dense object returning to find years have passed elsewhere. While the exact numbers depend on distance and mass, the principle is real. A neutron star could serve as a kind of time machine, not to travel backward, but to alter the rate of living forward. Step too close, and the universe outside leaves you behind. But this time, dilation is not only about the stars themselves, it plays a role in their interactions. When two neutron stars orbit each other, the flow of time is distorted in complex ways. The gravitational waves they emit carry with them the signature of time stretching and squeezing. Detecting those waves allows astronomers to study not only the stars' masses and spins, but also the relativistic effects that shape their merger. Time is written into the ripples of space itself. It also raises deep philosophical questions. If time flows differently in different places, what does it mean to say that two events happen at the same time? In relativity, simultaneity is relative, not absolute. Around neutron stars, this becomes strikingly obvious. An explosion on the surface may be nearly simultaneous with an observation far away, but the time measured between them depends on where you are. The universe does not keep a single, universal clock. It keeps billions, each tied to its own patch of space-time. The strangeness of time near neutron stars also connects to the boundary between them and black holes. In a black hole, time dilation becomes infinite at the event horizon. To an outside observer, anything falling in seems to freeze at the edge, never crossing. Neutron stars are the step just before that. They bend time dramatically, but not infinitely. They are the frontier where relativity becomes tangible, but not yet absolute. For astronomers, measuring these effects is more than curiosity. It allows them to test general relativity under conditions impossible elsewhere. The bending of time near neutron stars can be observed in the signals they emit, in the way their pulses shift, in the redshifts of their light. Comparing these observations with theory either confirms or challenges our understanding of gravity. So far, relativity has passed every test, but neutron stars continue to push the boundaries. It is remarkable to think that such an abstract concept as time can be bent, stretched, and altered. We live with the illusion of universality because our environment is gentle. Gravity here is mild, speeds are slow compared to light, and distances are manageable. But in the cosmos, especially near neutron stars, the illusion dissolves. Time itself becomes flexible, a variable shaped by the presence of mass. Imagine watching a pulsar spin, its beams flashing across the sky with perfect rhythm. Those flashes are already slowed by time dilation at the surface, already redshifted by gravity. What we see is not the pure rhythm, but the altered one, translated through curved space-time. Yet the precision is so great that even these distortions can be measured and accounted for. Pulsars become not only clocks, but also demonstrations of how time itself bends under gravity's grip. And as strange as all this may seem, it is only one part of the neutron star's story. Their density, their magnetism, their radiation, their collisions, all are intertwined with the way they bend time. Every feature of their existence is shaped by relativity. To study them is to study the nature of time itself, not as an abstract idea, but as a measurable, physical reality. When people hear about the strangest and most dangerous things in the universe, two names usually rise to the surface: neutron stars and black holes. Both are born from the collapse of massive stars. Both compress matter into conditions that defy ordinary intuition. Both are extreme in ways that stretch the imagination. Yet while they share some origins and qualities, they are not the same. One remains just on the edge of physical possibility, still visible, still tangible in some sense, while the other crosses that edge into invisibility and finality. The debate between neutron stars and black holes is not about which is more real. They both exist, confirmed by observation. The debate is about which is the deadliest, which is more extreme, and which represents the truest endpoint of stellar death. To start, consider their similarities. A massive star at the end of its life exhausts its nuclear fuel. Gravity overwhelms the outward pressure of fusion, and the core collapses. If the mass is in the right range, the collapse halts when neutrons push back, forming a neutron star. If the mass is greater still, even the neutrons cannot resist, and the collapse continues. Space and time fold inward, forming a black hole. Both are born in supernova, both are the corpses of stars, both are far denser than anything else in the cosmos. From a distance they might seem like variations on the same theme. Up close, however, the differences become stark. A neutron star, as extreme as it is, still has a surface. It is only about 12 miles across, yet it holds more mass than the Sun. Its crust is rigid, its interior a sea of neutrons or perhaps even stranger matter. It spins, it radiates, it quakes. You could, at least in theory, imagine approaching it, standing above it, measuring its emissions, studying its crust. You would not survive, of course. The gravity, magnetism, and radiation would tear you apart. But the object is still there, still part of our universe in a direct and observable way. A black hole, by contrast, has no surface. Its boundary is the event horizon, the point beyond which nothing, not even light, can escape. Once inside, all paths lead inward, and no information can return. To the outside universe, the black hole is defined only by its mass, its spin, and its charge. Everything else is hidden. It is not an object in the ordinary sense, but a region of space where the rules of physics bend beyond recognition. Which of these is deadlier depends on what you mean by deadly. The neutron star kills with proximity. Its gravity can spaghettify you long before you touch its surface. Its radiation can sterilize planets from light years away. Its magnetic fields can tear atoms apart. Yet it remains finite. It has a surface you can, in principle, describe. Its dangers can be measured and modelled. A black hole, on the other hand, is more absolute. Cross the event horizon, and you are gone from the universe's perspective. Time itself stretches, space folds, information is lost to the outside world. For a small black hole, the tidal forces at the horizon would rip you apart before you even crossed. For a super-massive black hole, the crossing might be more subtle. You could drift past the horizon without noticing anything at first. But the fate would be the same. The singularity at the centre, whatever it truly is, awaits. Whether matter there is compressed into a point or something more exotic, it represents an end beyond which physics as we know it cannot describe. The debate between neutron stars and black holes also highlights how finely balanced the universe can be. The line between them is a matter of mass. A star just heavy enough becomes a neutron star. A slightly heavier one becomes a black hole. The difference is measured in fractions of solar masses, yet the outcomes are completely different. One creates an object still accessible to study, the other creates a horizon beyond which nothing can be known. From a scientific perspective, neutron stars are often more useful. Because they are visible in X-rays, gamma rays and radio waves, they can be studied directly. Pulsars provide precise timing signals. Magnetars offer laboratories for extreme magnetic fields. Collisions of neutron stars reveal the origins of heavy elements. Each observation adds to our understanding of matter, magnetism and relativity. Black holes, by contrast, reveal less directly. They can be inferred from their gravitational pull, their accretion disks, their mergers, their shadows against glowing gas. But the interior remains hidden, forever beyond measurement. Yet in terms of sheer finality, black holes seem deadlier. They represent a one-way trip. Once past the horizon, there is no escape. Theories about what happens inside vary. Some suggest singularities, others propose quantum fuzziness, still others imagine that information is preserved in subtle ways. But none of these possibilities can be confirmed by observation. Neutron stars, by contrast, do not seal information away. They compress it, distort it, but they do not hide it completely. The danger to civilizations is another angle. A neutron star passing close to Earth would be catastrophic, yes. Its gravity would disrupt orbits, its radiation could strip atmospheres, its magnetic fields could fry electronics. But it would still be visible, still a known threat. A black hole, depending on its size, could be invisible until too late. A rogue black hole drifting through space could pass unnoticed, its presence betrayed only by gravitational lensing or the disruption of nearby stars. To encounter one would be to confront not just destruction, but invisibility, a danger that gives no warning. Still, both neutron stars and black holes play creative roles as well as destructive. Neutron star collisions forge heavy elements. Black hole accretion powers quasars, some of the brightest objects in the universe, influencing galaxy formation. Neither is simply a killer. Both are part of the ongoing cycle of creation and transformation in the cosmos. To label one as deadlier misses the subtlety. The debate is not settled because it depends on the lens you use. Visibility versus invisibility. Proximity versus finality. Finite danger versus infinite mystery. For astronomers, the comparison is also about frontiers. Neutron stars test our theories of matter at nuclear density. Black holes test our theories of gravity at its extremes. Both challenge physics in different directions. Neutron stars ask, how does matter behave when squeezed beyond atomic structure? Black holes ask, what happens when space-time itself collapses? Both questions remain open, and both drive the future of astrophysics. It is fascinating, too, to consider what happens when the two meet. Neutron star black hole mergers have been detected through gravitational waves. In these events, the black hole devours the neutron star, tearing it apart as they spiral together. Depending on the masses, some matter may escape, forging heavy elements, while the rest vanishes behind the horizon. These collisions combine the extremes, showing us both the matter-rich violence of neutron stars and the inescapable finality of black holes. They are reminders that the universe does not prefer one extreme over the other. It contains both, and sometimes it lets them interact. From the perspective of human imagination, neutron stars often feel stranger. They are tangible in ways black holes are not. You can imagine holding a teaspoon of neutron star matter, impossibly heavy. You can imagine standing on its crust, feeling the pull of billions of gravities. You can imagine its beams sweeping across space like cosmic lighthouses. Black holes resist such imagery. They are horizons, absences, voids. Their mystery lies in what cannot be pictured. This may make neutron stars more compelling to study, but it makes black holes more haunting. The debate, then, is less about declaring a winner, and more about appreciating two faces of cosmic death. Neutron stars are the survivors, the corpses that refuse to collapse further, holding themselves together with quantum forces. Black holes are the vanishing points, the stars that gave in completely, leaving behind only the pull of their mass. One continues to interact, to emit, to teach. The other erases, conceals, and leaves us guessing. Both, in their own ways, embody the extremes of the universe. And in that comparison lies the real fascination. Neutron stars show us what matter can do. Black holes show us what space-time can do. Together, they bracket the possible fates of massive stars. They remind us that the universe does not deal in moderation. It pushes to limits, explores edges, and reveals to us what lies there. Whether neutron star or black hole, the lesson is the same. Endings are not gentle, and the cosmos does not hesitate to bend its own rules. When a massive star dies, it leaves behind one of the most compact and extraordinary remnants in the universe. For a time, that remnant shines in ways its parent star never could, beaming pulses across the galaxy, shaking with quakes, bursting with radiation, colliding in cataclysms that forge the heaviest elements. But what happens afterward, when the pulses slow, when the quakes subside, when the bursts fade? Even the most dramatic lives of neutron stars do not last forever. They are not eternal. They have their own destinies, their own pathways into what might be called the cosmic graveyard. The first stage of a neutron star's life is usually active. If it is born with a strong magnetic field and rapid rotation, it may appear as a pulsar, sweeping beams across space like a cosmic lighthouse. For millions of years, these beams can be steady, precise, reliable. But with every pulse, the neutron star loses a little energy. Its spin slows, its beams weaken, and eventually it no longer has the strength to shine. It becomes what astronomers call a dead pulsar, a neutron star that no longer emits detectable radiation. Though invisible, it still exists, drifting silently through the galaxy. Some neutron stars become magnetars, their magnetic fields so strong they dominate their behaviour. For a few thousand to tens of thousands of years, they flare, quake, and burst. But magnetic fields decay, and over time magnetars lose their violent energy. They settle into quieter forms, becoming ordinary neutron stars once more, cooling and fading. Their fireworks are temporary. Their destiny, like pulsars, is to quiet down into obscurity. But even obscurity is not the end. A neutron star's ultimate fate depends on its environment. Some will remain alone, dark and quiet, forever drifting through space. These are the loneliest objects in the galaxy, no longer detectable except by their gravitational influence. Billions may exist in our Milky Way, unseen and uncounted, each a silent relic of a long-dead star. If one were to pass near the solar system, its gravity could disrupt planets or asteroids, yet we might never know until it was too late. These hidden wanderers are the ghosts of stellar death, populating the cosmic graveyard invisibly. Others have more dramatic fates. If a neutron star is in a binary system, its story may be extended by interactions with its companion. It may siphon matter, reigniting bursts of X-rays. It may spin up into a millisecond pulsar, recycling itself into a new form of activity. It may eventually merge with its companion, producing a killer nova and perhaps collapsing into a black hole. In such cases, the graveyard is not quiet. It is fiery, violent, and transformative. The neutron star does not simply fade away, but goes out in another blaze of energy. The possibility of collapse into a black hole is a particularly intriguing fate. If a neutron star accretes enough material from a companion, it can exceed the maximum mass that neutrons can support. At that point, no force in the universe can stop gravity from crushing it further. The star collapses into a black hole, crossing the boundary from visibility to invisibility, from matter to space-time. In this way, some neutron stars do not remain in the graveyard as neutron stars at all, but transition into something even more extreme. Others may collide with each other, as we have seen. These collisions scatter matter into space, forge heavy elements, and often leave behind black holes. The neutron stars themselves are destroyed in the process, their material either dispersed into the galaxy or swallowed by the singularity that forms. In these cases, the graveyard is not a place of quiet decay, but of violent transformation. The neutron star's final act is to give birth to gold, platinum, uranium, and countless other elements, enriching the universe before vanishing forever. Even for those that do not meet such dramatic ends, the process of cooling itself is fascinating. A newly formed neutron star is incredibly hot, with temperatures reaching hundreds of billions of degrees, but it cools rapidly, radiating neutrinos from its interior and photons from its surface. Within a few million years it becomes cold and dark, invisible to most telescopes. What remains is a sphere of degenerate matter, no longer active, no longer emitting detectable light, yet still dense, still massive, still exerting gravity. These cold neutron stars are perhaps the truest residents of the cosmic graveyard, silent monuments to the deaths of stars. The graveyard is not empty, it is likely crowded. Estimates suggest there may be as many as 1 billion neutron stars in our galaxy alone. Most are invisible to us, their pulses long gone, their surfaces cooled. They drift quietly among the stars, their presence betrayed only when they happen to interact with something else, when they pass in front of background stars, bending light with their gravity, or when they collide with companions. Otherwise, they are hidden. The night sky we see, full of stars, is only half the truth. For every star we see shining, there may be many neutron stars lurking unseen, the dead outnumbering the living. This realization changes how we think about the galaxy. It is not only full of light and energy, but also full of relics, corpses of stars that once burned brightly. The cosmic graveyard is not a distant place, but an ever-present reality. We live among ghosts, our solar system drifting through a galaxy filled with the remains of stars long gone. Some of those remains have already touched us, their matter incorporated into Earth and into our own bodies. Others pass silently by, unnoticed. The graveyard is not something to fear, but something to acknowledge as part of the natural cycle of the universe. There is a kind of symmetry in this. Stars live, burn, and die. Their remnants drift, fade, and sometimes transform again. The graveyard is not final, but transitional. Neutron stars may cool into obscurity, but their matter is still there, still part of the galaxy's mass. Collisions may destroy them, but the elements they scatter become part of new stars, planets, and life. Even when they collapse into black holes, they continue to shape the universe through their gravity. Nothing is wasted. Even in death, neutron stars continue to contribute. For astronomers, the challenge is to find and study these remnants. Active pulsars and magnetars are relatively easy to detect, but the vast majority of neutron stars are dark. New techniques, such as gravitational lensing surveys and gravitational wave detectors, may one day reveal more of them. Each discovery adds to our understanding of how many stars die, how often, and what becomes of their remains. Mapping the cosmic graveyard is a task still in its infancy, and so the question of where neutron stars end up is not answered with a single fate, but with many. Some become quiet wanderers, drifting invisibly through space. Some are reborn as millisecond pulsars. Some collapse into black holes. Some collide in fiery mergers. Some cool into silence. The graveyard is vast, varied, and full of stories. It is not a final resting place so much as a stage in an ongoing cycle, where endings become beginnings, and even the most silent objects still shape the galaxy. For most of human history, neutron stars were invisible to us, not only because they're faint and small, but because we didn't even know they could exist. The sky was filled with points of light, some wandering, some steady, but all of them seen only in visible wavelengths. To the human eye, a neutron star does not stand out. It does not glow brightly like Sirius. It does not flare like Venus at dawn. It does not stretch across the sky like the Milky Way. To us, it is almost nothing, a hidden relic. And yet today, we know of their existence, their properties, and their roles in the universe. The bridge from ignorance to understanding was built with telescopes, detectors, and the human determination to see beyond what our senses allow. The story of neutron stars is inseparable from the story of astronomy itself. Telescopes opened the heavens in visible light, revealing planets, moons, galaxies, and clusters. But neutron stars reveal themselves in other ways, mostly invisible to our eyes. They shine in radio waves, in X-rays, in gamma rays. To find them, we had to invent new kinds of telescopes, instruments that did not simply magnify light, but translated the universe into frequencies humans could never see unaided. Every new window we opened revealed new surprises, and neutron stars were among the most startling. Their discovery in the 1960s came almost by accident. Jocelyn Bell Burnell, a graduate student at the time, was monitoring radio signals with a large array of antennas. She noticed a strange signal, a regular series of pulses repeating with astonishing precision. At first, the team wondered if it might be interference, or perhaps even an artificial source. The signal was so regular that they jokingly labelled it LGM for Little Green Men. But soon it became clear that this was not a message from extraterrestrials. It was something natural, something new, something no one had predicted. The first pulsar had been found. That discovery revolutionised astrophysics. Suddenly, the idea of neutron stars, which had been a theoretical possibility, became an observational reality. The pulses were too precise, too stable to come from anything else. Here were the remains of massive stars, spinning at incredible speeds, sweeping beams of radiation across space. Telescopes had captured the heartbeat of dead stars, turning theory into fact. Since then, the search for neutron stars has expanded across the electromagnetic spectrum. Radio telescopes continue to be essential, detecting the rhythmic pulses of many neutron stars. Giant dishes like those at Arecibo, Parkes, and Greenbank have catalogued thousands of pulsars, each with its own unique rhythm. These signals travel across light years to reach us, arriving faint but clear enough to be picked out from the cosmic noise. The precision of these pulses allows astronomers to study everything from stellar interiors to gravitational waves, turning radio astronomy into a tool for fundamental physics. X-ray telescopes have opened another window. Instruments in orbit, above Earth's atmosphere, detect the glow of accreting neutron stars, the burst from their surfaces, the steady emissions from their hot crusts. Missions like Chandra, XMM Newton, and NISA peer into regions invisible to ground-based observatories, revealing neutron stars as bright X-ray sources in binary systems. These telescopes show us how neutron stars feed on their companions, how they flare with thermonuclear fire, how they glow faintly as they cool. Without them, much of the neutron star story would remain hidden. Gamma-ray observatories add yet another perspective. The Fermi Gamma Ray Space Telescope, for example, has identified pulses that emit not only in radio but in high-energy photons. These gamma-ray pulses reveal the extremes of particle acceleration, the magnetic storms of magnetars, the sudden flares that ripple through space. The invisible universe becomes visible in data streams, graphs, and images that translate raw energy into knowledge. And telescopes are not limited to light. Gravitational wave detectors like LIGO and Virgo have extended our senses to vibrations in space-time itself. With these instruments, humanity has felt the ripples of colliding neutron stars, adding sound to sight in a sense, a new way of perceiving the universe. The 2017 detection of G70817 marked the beginning of this era. Telescopes across the world coordinated to capture the light from the same event, proving that neutron stars not only emit in radiation, but also shake the fabric of reality itself. The collaboration between different telescopes is what makes discoveries possible. No single instrument can capture the whole story. Radio arrays listen for pulses, X-ray observatories record flares, gamma-ray detectors catch bursts. optical telescopes trace kilonova light curves. Gravitational wave detectors pick up the rumble of mergers. Together they form a symphony of observation, each instrument a different section of the orchestra, each contributing to the larger music of the cosmos. Without this cooperation, neutron stars would remain half-hidden. With it, they are revealed in astonishing detail. The progress of telescope technology has also changed our place in the story. Early astronomers sketched what they saw by eye. Later, photographs preserved faint galaxies and nebulae. Today, data streams feed into computers, processed by algorithms, analysed by teams across continents. Discoveries are no longer the work of a single observer at a single instrument, but of networks, collaborations, and shared effort. Neutron stars are found not by one person looking up, but by many people working together, pooling knowledge and technology to see farther. Even so, the human element remains. The careful attention of Jocelyn Bell Burnell noticing an anomaly, the persistence of teams developing detectors sensitive enough to catch faint ripples, the creativity of engineers building satellites and arrays. All of this is part of the story. Telescopes are extensions of human curiosity, tools that carry our senses beyond their natural limits. Without them, neutron stars would remain invisible. With them, they become part of our shared knowledge of the universe. Future telescopes promise even more. The square-kilometre array, under construction, will survey the radio sky with unprecedented sensitivity, likely discovering tens of thousands of new pulsars. The James Webb Space Telescope, though focused on infrared, may contribute by studying the aftermath of neutron star collisions. New X-ray missions such as Athena are planned to probe compact objects in greater detail. Even more advanced gravitational wave detectors, like the Einstein Telescope and LISA, will expand our ability to feel the universe. Each new instrument will sharpen our picture. Each will reveal more of the graveyard of stars. It is worth remembering that all of this effort comes from a simple desire: to know. Neutron stars do not reveal themselves easily. They are faint, small, hidden, extreme. To find them, we had to stretch technology to its limits, building instruments capable of detecting the faintest signals across vast distances. The fact that we can do this, that human eyes and minds can reach across light years to study collapsed stars, is as remarkable as the objects themselves. When you consider the progress, it is astonishing. Just a century ago, neutron stars were not even imagined. In the 1930s, a few theorists speculated they might exist, but there was no evidence. By the 1960s, their pulses had been discovered. By the 1990s, their X-ray and gamma-ray emissions were well catalogued. By the 2010s, their collisions were detected through gravitational waves, and in the coming decades we may map their interiors, measure their equations of state, and discover thousands more. In only a few generations we have gone from ignorance to intimate knowledge, all through the power of telescopes and the determination to see. And yet there is always more to find. Every new telescope uncovers surprises. Some pulsars behave unpredictably, glitching suddenly. Some magnetars flare without warning. Some neutron star mergers produce unexpected light curves. Each anomaly pushes us to refine our models, to question assumptions, to look again with sharper instruments. The process never ends. The universe continues to surprise us, and neutron stars are among its most surprising actors. In the end, telescopes are more than tools. They are bridges. They connect human eyes to the infinite, human thought to cosmic reality. They turn invisible pulses into visible graphs, distant bursts into data, vibrations in space-time into signals we can measure. They remind us that our senses are not fixed limits, but starting points. With glass, metal, electronics and creativity, we have extended those senses into realms our ancestors could never have imagined. And through those extensions, neutron stars have emerged from invisibility into clarity. For as long as people have looked up at the sky, they have tried to weave meaning into the stars. Constellations became animals, hunters, heroes. Planets became gods moving against the background of the fixed stars. Comets were omens. The night sky was not just a map of lights, but a canvas for stories, a place where imagination met mystery. And even now, when we know more about what stars are and how they live and die, the urge to find poetry in them has not disappeared. Neutron stars, though discovered only in the last century, have already become part of that tradition. Their very existence is a metaphor, a symbol, a reminder of how beauty and destruction can be bound together in the same object. Think about the way they are born. A massive star lives for millions of years, burning hot and bright, shaping its surroundings with light and wind. Then, in a final collapse, it explodes, casting its outer layers into space. What remains is not a glowing orb, but a tiny remnant, the core crushed into a city-sized sphere of neutrons. It is death and survival at once, an end and a continuation. From one perspective, the star is gone forever. From another, it still exists, transformed, concentrated, hardened into something new. This duality invites metaphor. It is the phoenix story retold in physics, the rebirth of fire into ash, and of ash into something enduring. The beams of pulsars add another layer. These lighthouses of the cosmos sweep their signals across space, with a regularity so precise it rivals atomic clocks. To scientists, they are data, evidence, tools for measuring relativity and the structure of matter. But to anyone listening for meaning, they are heartbeats, ticking reminders that even dead stars still pulse with rhythm. They are drums in the cosmic night, beating steadily long after the fire is gone. The idea that death is not silence but rhythm resonates with human imagination. It turns neutron stars into symbols of persistence, endurance, and the strange ways in which endings can still carry life. Magnetars, with their violent flares, suggest yet another image. They are stars that cannot contain themselves, their magnetic fields so strong they twist and snap, releasing bursts that light up detectors on Earth. To describe them in human terms, they are tempests bottled inside corpses, storms that rage long after the skies have gone dark. The metaphor of storm fits easily, and the poetry almost writes itself. Yet behind it lies the truth of physics, that magnetic fields, usually gentle and familiar, can become monstrous when amplified to cosmic scales. Even the collisions of neutron stars carry mythic weight. Two stars locked in orbit, spiralling closer and closer, until they finally collide in a burst of light and gravitational waves. From their destruction comes gold, platinum, uranium, the elements that shape planets and civilizations. The metaphor is irresistible. From death comes creation, from ruin comes treasure. Every ring, every crown, every circuit in modern devices carries that story. The poetry is not invented, it is written into the atoms themselves. Cultures have always connected the heavens to human life. Myths about dying stars are as old as mythology itself. The idea of a god who dies and is reborn, of cycles of destruction and renewal, echoes the astrophysical cycles of supernovae and neutron stars. The difference now is that we can tie the metaphors to physical reality. We know the mechanisms. We can measure the pulses, detect the waves, trace the origins of elements. Yet the scientific knowledge does not erase the poetry. If anything, it deepens it. The stories we tell are no longer just guesses, but reflections of truth that the universe itself has revealed. The metaphor of the grave also fits easily with neutron stars. They are the corpses of stars, the remnants of stellar lives, buried not in soil but in space. Yet they are not quiet graves. They burst, quake, flare, and collide. They remind us that death is not always stillness. Sometimes it is activity, sometimes it is transformation, sometimes it is the beginning of new things. That is a powerful metaphor for human experience as well. The idea that endings can give way to unexpected continuations. Even the smallest details of neutron stars carry symbolic weight. A teaspoon of their matter outweighs mountains, reminding us that appearances can deceive, but density and importance are not always visible on the surface. Their crusts, stronger than steel, suggest resilience. Their spins, sometimes hundreds of times per second, suggest urgency and persistence. Their quakes, sudden and violent, suggest that even the strongest structures can break under stress. The metaphors practically unfold themselves, waiting only for human imagination to notice them. The cultural impact of these stars is only beginning. Already musicians have turned pulsar signals into rhythms, artists have painted neutron star collisions, writers have used them as symbols of endurance, destruction, or mystery. Just as black holes have become metaphors for loss, for inevitability, for the unknown, neutron stars are becoming metaphors for resilience, for hidden strength, for the strange balance of creation and destruction. In time, they may take their place alongside the constellations and myths of old, woven into stories not of gods and heroes, but of the universe itself. But the poetry is not only in how humans describe them, it is also in how they behave. The rhythms of pulsars, the sudden flares of magnetars, the collisions that create new elements, these things are already stories, already patterns. When astronomers translate data into sound, the clicks and beats of pulsars sound like music. When telescopes catch a kilonova, the light curve is like a narrative, brightening, peaking, fading. The universe tells stories whether we listen or not. Our role is simply to notice them, to frame them in ways that resonate with our own lives. There is something comforting in this. In the vastness of space, neutron stars are indifferent. They do not care about human meaning, yet they still embody themes that humans have always cared about: death, persistence, transformation, hidden strength. To find those themes written in the sky is to feel a connection, a reminder that our lives, small as they are not separate from the cosmos but part of it. The metaphors are not forced, they are discovered, uncovered, revealed in the light and pulses of dead stars. This blending of science and poetry is not new. Galileo saw mountains on the moon and compared them to earthly landscapes. Kepler described the harmony of planetary motions as music. Today, we speak of neutron stars as lighthouses, as graves, as drums, as storms. The metaphors help us grasp what numbers and equations alone cannot convey. They remind us that understanding is not only about measurement but also about meaning, and so neutron stars occupy a special place in our imagination. They are both scientific objects and poetic symbols, both data and metaphor. They teach us about physics while reminding us of stories we have always told, that endings are beginnings, that strength can be hidden, that rhythm persists after silence. In their beams and bursts, in their collisions and quakes, we see not only astrophysics but also echoes of our own experience. When we study neutron stars, the questions seem at first to belong purely to astrophysics. How dense can matter become before collapsing into a black hole? How strong can a magnetic field be? What happens when two compact stars collide? These are technical questions measured in equations, charts, and observations. Yet it is difficult to spend time with neutron stars, even in imagination, without turning the questions inward. They are not just curiosities in the sky. They are mirrors, in a way, reflecting truths about endurance, fragility, transformation, and perspective. In studying them, we inevitably end up studying ourselves. Start with the idea of pressure. A neutron star exists because gravity crushed a star's core beyond the resistance of atoms. Electrons were forced into protons, forming neutrons, and the result was a new equilibrium at staggering density. What this teaches us is that even when structures collapse, something new can emerge. Atoms gave way to neutrons, but the star did not vanish entirely. It transformed into something strange yet stable. In human life, pressure takes many forms: social, emotional, personal, and while we cannot compare it literally to the crushing gravity of a supernova, the metaphor resonates. Pressure changes us, sometimes in ways that break old structures, sometimes in ways that reveal new strength. Neutron stars also remind us that appearances can deceive. To the eye, they are invisible, faint, no brighter than any other patch of sky. Yet within that invisibility lies mass greater than the sun. A teaspoon of their matter outweighs mountains. They teach us that what is hidden may hold enormous significance. In people too, so much is unseen. Thoughts, struggles, resilience that cannot be measured at a glance. The lesson is that value is not always on the surface. Density of experience, depth of character, strength under pressure, these are things that may be invisible but are no less real. Their rhythms speak to us as well. Pulsars tick with astonishing regularity, some spinning hundreds of times per second without missing a beat. They become cosmic clocks, their precision rivaling human-made timekeepers. To scientists, this is useful for navigation and measurement. To the imagination, it is a reminder of consistency, of endurance. Even after death, a star can keep rhythm. Even after collapse, it can send steady signals across light years. There is something deeply human in finding reassurance in rhythm, in regularity and persistence. We know it from music, from heartbeat, from routine. Neutron stars embody it on a cosmic scale. Magnetars add another lesson, though in a different way. Their magnetic fields are so intense that they sometimes snap, releasing flares of radiation visible across galaxies. They are stars that cannot hold all their tension quietly. They store stress until it erupts. This too feels familiar. People can be strong, resilient, enduring, but no one is unbreakable. Under enough stress, we flare, we quake, we release energy suddenly. Neutron stars remind us that even the strongest structures have limits, and that release, though violent, is part of existence. It does not mean weakness. It means the laws of nature apply everywhere, from stars to humans. Collisions of neutron stars teach us about creation in the aftermath of destruction. When two collide, they forge gold, platinum, uranium, the elements that enrich planets and civilizations. The message is clear. Endings are not just loss, they can also be beginnings. Destruction can scatter seeds for future creation. In human life, this too is true. Failures, losses, endings often feel final, but they can be the source of new growth, new opportunities, new stories. The universe models this for us in its most dramatic moments. Even the way neutron stars bend time has a human echo. Near their surfaces, time runs slower relative to the outside universe. It is a strange fact of relativity, yet it resonates metaphorically. We all experience time differently. A moment of joy can feel stretched, a moment of pain elongated, a year of routine compressed. The physics of relativity and the psychology of perception are not the same, but the resonance is striking. Both remind us that time is not as rigid as it seems. Its flow depends on perspective, on position, on context. The silence of most neutron stars also carries a lesson. Only a fraction are active as pulsars or magnetars. The rest are invisible, cold, drifting quietly through the galaxy. They teach us that not all influence is loud or visible. Presence itself has weight. A quiet person in a room can change its atmosphere. A silent star in a galaxy can shape orbits with its gravity. What is unseen can still matter profoundly. Neutron stars also remind us of the importance of perspective. From afar they are invisible. With the wrong tools they do not exist. Only with radio telescopes, X-ray satellites, gravitational wave detectors do they reveal themselves. The lesson is that our tools shape what we see. In life too, perspective and attention determine what is visible. With patience, curiosity and the right lens, hidden truths emerge. Without them, whole worlds remain invisible. The sheer extremes of neutron stars also challenge our sense of possibility. They show that the universe does not hesitate to push physics to its limits. Density beyond imagination, magnetism beyond measure, collisions that shake space-time. These things exist, not in theory, but in reality. For humans, the lesson may be humility. The universe is stranger, larger, more extreme than our daily lives suggest. Our struggles, while real, exist within a vast context that dwarfs them. This is not to minimize human experience, but to remind us of perspective. We are part of a universe capable of astonishing things. Our existence is one thread in that vast fabric. There is also a lesson in resilience. Neutron stars endure for billions of years. Their pulses slow, their flares fade, their heat diminishes, but they remain. Long after their parent star is gone, long after their supernova fades, the neutron star persists. It is a reminder that survival can look different from flourishing, that endurance itself has value. Even when activity fades, presence remains. And yet they also teach impermanence. Even neutron stars are not eternal. They may collapse into black holes if they gain mass, or they may merge and be destroyed. Even the densest, strongest objects eventually meet transformation. The lesson is that nothing lasts forever. Not stars, not galaxies, not even the universe as we know it. This impermanence is not tragic. It is natural. It is the rhythm of existence. Recognizing it can change how we see our own lives, not as failures when things end, but as participation in the larger cycle of transformation. When telescopes capture the pulses of neutron stars, the signals are often converted into sound for analysis. What emerges is a steady beat, like a drum or a clock. To hear it is to realize that the universe already contains rhythms we can recognize. We are not separate from them. Our music, our poetry, our heartbeat all reflect rhythms that exist on cosmic scales. Neutron stars remind us that connection runs deep, from our biology to the remnants of exploded suns. In the end, the greatest lesson may be humility paired with wonder. Neutron stars do not exist to teach us, but by studying them we learn. We learn that strength can hide in smallness, that pressure transforms, that silence still carries weight, that destruction can be creative, that endurance is real but impermanence is inevitable. They do not tell these lessons in words but in pulses, in quakes, in collisions, in silence. Our role is to listen, to interpret, to find meaning in the signals. We've travelled far together tonight, tracing the story of collapsed stars across pulses, quakes, bursts, collisions, and mysteries. As you listen now, you may feel the weight of it all, the sheer scale of these objects that crush entire suns into spheres smaller than cities. Yet even in their enormity there is something soothing. The universe does not rush. It unfolds slowly, patiently, over millions and billions of years, and in that patience there is comfort. Think about where you are right now. The room around you is calm, steady, familiar. And above that room, above the roof, above the atmosphere, above the orbit of satellites, lies a galaxy filled with stars, some living, some dying, some long dead. Among them are neutron stars scattered across the Milky Way like hidden relics, invisible to the eye but real nonetheless. They are drifting, pulsing, sometimes colliding, sometimes fading into silence. And though they are unimaginably far, their signals have reached us. Their pulses, their flares, their gravitational ripples, all have arrived, faint but certain, carrying their story across light years. There's something gentle about imagining them now, not as threats or catastrophes, though they certainly can be, but as companions in the night sky, quiet, steady presences. They remind us that even after endings, something remains. The massive stars that birthed them are long gone, their light faded, their gas scattered, but the neutron stars persist. They are survivors, holding together against all odds, small yet impossibly dense, fragile in some ways, indestructible in others. As you lie here, you might picture one, turning slowly in the darkness, its beams sweeping across the void. Each rotation, each pulse, is like a breath, steady and rhythmic, You can imagine syncing your own breathing to it, in as the beam sweeps by, out as it passes into shadow. The star is unimaginably distant, yet in that simple rhythm you find connection. The cosmos offers you a pattern to rest with, a reminder that even in vastness there are regularities, consistencies, comfort in repetition. And when you think of the collisions, the great bursts that create gold and platinum, you might find comfort in that too. Because it means that the atoms around you, the ones in your jewellery, in your phone, in your blood, come from those collisions. You're not separate from these stars. You carry them with you, not metaphorically but physically. They are part of your body, your mind, your existence. To rest beneath them is to rest within them as well, because their story is your story. You might wonder what it feels like to drift near one. Imagine being in a spacecraft, far enough away to be safe but close enough to see the glow. The neutron star spins, its light beams out, its surface crust creaks under stress. Around it, space is bent, time is stretched. It is both alien and strangely familiar, because what it represents, endurance, transformation, persistence, are things you already know. You drift there, suspended in silence, and you realise that the universe is not hostile. It is simply vast, simply strange, simply itself. And within that vastness you find calm. Even the most violent events, the starquakes and magnetar flares, fade eventually. What is left afterward is quiet. A star cracks, bursts, then rests again. A collision lights up a galaxy, then settles into embers. A pulsar ticks for millions of years, then slows into silence. Everything is active for a time, then it rests. You too are part of that rhythm. Activity and rest, tension and release, energy and quiet. The stars model it, and so do you. There is no rush in this story. Neutron stars live for billions of years. Their pulses may slow, but slowly. Their collisions may be rare, separated by millions of years. Even their deaths, their collapses into black holes, unfold at the pace of the cosmos. You can let yourself be carried by that slowness. There is time for everything. There is space for everything. And for you, right now, there is space for rest. Close your eyes, if they are not closed already. Picture the Milky Way stretched above you, its billions of stars woven into a soft band of light. Among them are the hidden ones, the neutron stars, tiny and dense, silent and steady. They do not shine like the others, but they are there, holding their place, shaping the galaxy with invisible weight. Imagine drifting among them, floating weightless in the calm of interstellar space. The cold is immense, but you are safe, cocooned, watching the stars turn slowly around you. You pass a pulsar, its beams sweeping in rhythm. You listen, and it becomes a lullaby, a steady ticking that slows your thoughts. You pass a magnetar, its field vast but quiet at the moment, a sleeping giant in the dark. You pass the remnants of a collision, glowing faintly with the heavy elements scattered into space, the building blocks of worlds. Each one reminds you that the universe is full, not empty, that even in death there is richness, that even in silence there is weight. The more you picture it, the smaller your worries may feel. Not in a dismissive way, but in a freeing way. The universe is vast, and yet it makes space for everything, from the largest explosions to the smallest concerns. Whatever is on your mind can rest for now. It can wait. The neutron stars wait too for billions of years, without rushing, without pressing. You're allowed the same patience. Breathe again with the rhythm of the stars. In, steady, calm. Out, slow, gentle. Imagine that each breath is connected to the pulses arriving from light years away. You're synchronized with the cosmos, not because you must be, but because you can be. It is there, available, ready to be listened to. And as you drift deeper into rest, let the thought of those stars accompany you. They are the universe's heaviest dreams, condensed into tiny spheres, yet carrying the weight of entire suns. They rest in silence now, as you are about to rest. They remind you that stillness has its own power, that quiet is not emptiness but fullness, that rest is not absence but presence. You are safe here, under their watch. The cosmos is vast, but it is steady. Its rhythms are slow, its changes patient, its extremes softened by distance. You are part of that cosmos, carrying its elements, breathing its air, living in its time. Tonight you can let yourself feel that connection and let it guide you into calm. And as you drift, remember that even the dead stars still shine in their own way. Even the quiet ones still hold weight. Even the collapsed ones still shape galaxies. You too hold weight. You too matter, even in stillness, even in rest. So rest now, beneath the universe's heaviest dreams. Thank you for being here tonight, for giving your time and attention to this journey through the stars. If you found peace in these stories, or if the calm rhythm of the universe has helped you rest, you're always welcome to return. You can close your eyes now and let go of the need to listen closely. The stars will keep spinning, the pulsars will keep ticking, the universe will keep unfolding, and you can simply rest within it. If you'd like more nights like this, more quiet explorations of science and wonder, you can stay connected by subscribing or by leaving a small sign that you are here. But for now, there is nothing you need to do. Just breathe, feel safe, and let sleep take you, gently and easily. Good night, and may your dreams be as steady as the pulses of the stars.